What lies beyond the edges of our cosmic neighborhood? It's a question that has inspired scientists, explorers, and dreamers for generations. Beyond the planets of our solar system, and even the glittering expanse of our galaxy, there are realms so vast and unknown that they defy imagination. From the faint traces of high-speed stellar streams at the Milky Way's outskirts, to the enigmatic isolated neutron stars drifting in intergalactic space, the universe is filled with secrets waiting to be uncovered. Each of these mysteries tells a story about what lies far beyond, where science fiction often meets science fact, and the boundaries of knowledge are constantly being redrawn. HL Tauri protoplanetary disk. The HL Tauri protoplanetary disk lies about 450 light-years away, but its details offer insights that stretch across time and space. This young star, no more than 1 million years old, presents a surprising level of complexity in its disk, far more developed than expected. Observations show concentric rings and sharp gaps that suggest the presence of newborn planets carving their paths through the dense material. These planets, hidden but revealed by their gravitational influence, may be forming faster than current models predict. The clarity of these features has pushed scientists to rethink timelines for planetary formation, challenging long-held assumptions. The dust within HL Tauri's disk doesn't settle uniformly. Larger grains are concentrated closer to the star, while finer particles spread outward, a pattern that hints at dynamic forces shaping the system. Dust-to-gas ratios in this disk are unusually high, suggesting chemical processes distinct from those observed in older systems. These ratios not only affect the disk's evolution, but could also determine the type of planets that form, influencing their compositions and atmospheres. Snowlines within the disk, where compounds like water or carbon dioxide freeze, mark zones of distinct chemical activity. These frozen regions play a crucial role in defining the makeup of future planets, as volatiles accumulate and solidify, providing the raw materials for planetary cores and atmospheres. Closer examination of the disk reveals peculiarities in the distribution of material. Some gaps are wider than expected, suggesting gravitational instabilities that might fragment the disk itself. These instabilities could lead to the formation of gas giant planets, a process different from the slow buildup of rocky cores. Gas flows through the gaps, moving toward the star, may also hint at young planets shepherding material as they grow. This movement is not random, but shaped by the complex interplay of forces, including gravity and radiation. The disk itself appears to be losing material through faint winds, which further alter its structure and may limit how much material remains for planet formation. The behavior of HL Tauri's disk mirrors some processes observed in distant regions of the universe, such as the cold spot in the cosmic microwave background. Both involve dynamic interactions that reveal hidden influences shaping their structures. The cold spot, a region unexpectedly cooler than its surroundings, may indicate a supervoid or even a glimpse of phenomena beyond the observable universe. Similarly, HL Tauri's gaps and rings are shaped by forces that are not immediately visible but leave clear imprints in the disk's structure. These patterns remind us that unseen processes often drive the evolution of cosmic systems. Much like HL Tauri, brown dwarfs occupy an ambiguous space, existing between stars and planets. Found in nearby galactic systems, these objects challenge our understanding of star formation. Their masses are too low to sustain nuclear fusion, yet they form in ways that resemble stars rather than planets. The study of brown dwarfs, particularly those in neighboring galaxies, sheds light on how small variations in mass and environment can lead to vastly different outcomes in celestial objects. These dwarfs, with their faint glows, serve as cosmic laboratories, offering clues about conditions that may also influence disks like HL Tauri's. Microlensing events near the galactic halo provide another window into unseen structures. When a massive object passes between Earth and a distant star, its gravity bends the light, magnifying the background star's brightness temporarily. These events have revealed planets, black holes, and even rogue stars drifting in interstellar space. The technique could be applied to HL Tauri-like systems to detect planets too faint or too small to see directly, offering a complementary method to study distant protoplanetary disks. Instruments capable of detecting Cepheid variable stars extend our reach further into the universe. These stars pulsate with predictable brightness cycles, allowing astronomers to measure vast cosmic distances. Their reliability has made them essential tools for mapping the universe's scale. Similarly, HL Tauri's disk serves as a map, marking stages of planetary formation and providing benchmarks for comparing other young systems. By studying these stages, scientists refine models of how stars and their planetary systems evolve. Molecular clouds at high latitudes in the Milky Way hold reservoirs of organic material and cold gas. These clouds, like the material surrounding HL Tauri, are nurseries of chemical activity. Observations of such regions provide a glimpse into the early stages of disk formation, where molecules coalesce under gravity, setting the stage for star and planet formation. The presence of organic compounds in these environments raises the possibility of prebiotic chemistry, linking the building blocks of life to the earliest phases of planetary development. Gravitational anomalies in the local void, a massive region near our galaxy with few galaxies, mirror the puzzling dynamics within HL Tauri's disk. Both involve forces that defy expectations, requiring new explanations to account for their behaviors. The local void's lack of gravitational pull affects galaxy motion, while in HL Tauri, the forces shaping its rings and gaps suggest interactions beyond simple gravitational models. Gamma-ray halos around active galactic nuclei, AGN, offer another parallel. These halos, formed by energetic particles escaping the intense environments around AGN, spread across vast intergalactic distances. Their study provides insights into energy transfer and particle acceleration on large scales. Similarly, HL Tauri's disk winds, faint but measurable, reveal how energy and material flow within young stellar systems, shaping their evolution in subtle but significant ways. The neutron stars that are discovered alone in interstellar space are very different from the disk of stars in HL Tauri. While studying these supernova remnant stars, which have very little interaction with their environments, we can learn about the basic mechanisms of stellar development. As an exception to the solitary neutron star, HL Tauri exhibits dynamic and continuous interaction with its disk. There are certain parallels between the material being expelled from HL Tauri's disk and the massive gas outflows known as the Fermi bubbles, which originate from the center of the Milky Way. Whether it's a newborn star or the galactic center, both processes include the motion of gas propelled by energy releases. Energy has the ability to alter cosmic settings, impacting areas far from their sources. These structures, on incredibly diverse scales, show this. Ultra-faint dwarf galaxies orbiting the Milky Way hint at the delicate balance of forces in their formation, much like the finely tuned structure of HL Tauri's disk. These galaxies, with their sparse star populations, may represent remnants of ancient cosmic interactions, preserving details of the universe's early history. HL Tauri, though young, serves a similar purpose by preserving the stages of planetary birth, offering a glimpse into processes that occurred in our own solar system billions of years ago. The discovery of hyperfaint globular clusters on the Milky Way's outskirts provides another layer of connection. These clusters, holding some of the oldest stars, act as time capsules for the galaxy's history. Similarly, HL Tauri's disk acts as a time machine, showing what our solar system might have looked like in its earliest days, frozen in its youth for us to study. Neutral hydrogen bridges between galaxies serve as conduits for material transfer across cosmic distances. These bridges, invisible to the naked eye but detectable through radio telescopes, parallel the movement of material within HL Tauri's disk. Just as hydrogen flows between galaxies, dust and gas flow within the disk, feeding the young star and shaping its planetary system. In contrast to the newborn worlds developing within HL Tauri's disk, rogue planets are lost and floating aimlessly. It is worth noting that these planets may have been expelled from their systems, illustrating how planetary systems may be formed or destroyed by dynamic processes. On the other hand, HL Tauri is a system that is being assembled, not disassembled. Theoretical cosmic islands, isolated regions of matter beyond the main galactic filaments, might hold ancient remnants of the universe untouched by expansion. These islands offer a glimpse into a different aspect of cosmic evolution, akin to how Tauri provides a snapshot of early planetary formation, each revealing a piece of a much larger puzzle. A lone pulsar's consistent emissions serve as a cosmic marker, similar to how the holes in Tauri's disk indicate the existence of hidden planets. The meticulous mapping of Tauri's disk and the accuracy of pulsar observations both provide insights into the dynamics, interactions, and hidden influences that shape these objects' surroundings. As Tauri's system evolves, it remains a vivid example of how stars and planets form, showing that even in its youth, a system can reveal connections that span across the universe. Its gaps and rings are more than just features. They are windows into the processes that have shaped not only its destiny, but potentially the entire cosmos beyond. The cold spot. How planets originate is shown by the complex structure of Tauri's protoplanetary disk, but what occurs on the cosmic scale can be equally intriguing and mysterious. Mystery regions like the cold spot in the cosmic microwave background, CMB, are examples of this. It stands out from the usually homogeneous Big Bang backdrop and seems to be a colder than expected location. Because of its massive size and noticeable temperature anomaly, this object, which is located 1.8 billion light-years away, complicates current theories about the early cosmos. The cold spot is colder by about 70 microkelvins compared to the surrounding CMB. While this difference may seem small, it's significant enough to demand an explanation. One hypothesis suggests it could be a supervoid, a region of space so vast and empty that it reduces the gravitational lensing effect on photons traveling through it. As light from the CMB passes through this emptiness, it loses energy, creating the cooler appearance. However, even a void this large shouldn't be able to account for the full extent of the temperature drop. This gap between theory and observation fuels speculation. A number of hypotheses place the early universe's inflationary phase. Inflation may have caused quantum fluctuations to be magnified by fast expansion, which in turn may have left behind density anomalies. It is possible that the cold spot is a frozen remnant of a past variation of this kind, but even in this case, the models imply that it would remain an anomaly, an extremely unusual occurrence that defies simple explanation by chance alone. If it exists, it may cause the mainstream cosmological model to collapse, suggesting the presence of hidden processes. Others look to the multiverse for answers. In this context, the cold spot could be a bruise, evidence of our universe colliding with another during its formation. If universes can interact, the energy from such a collision might have imprinted itself on the CMB, leaving behind this anomaly. While this idea is speculative, it's not entirely without merit. If confirmed, it would upend our understanding of the cosmos, expanding it beyond the boundaries of a single universe. After a closer look, another intriguing aspect becomes apparent. The cold spot isn't a random area. It exhibits characteristics of a non-Gaussian distribution. The patterns within it deviate from the random fluctuations that characterize the rest of the CMB. This non-Gaussian behavior further complicates matters, raising the possibility that it may have originated from isolated events rather than cosmic processes on a global scale. Some researchers propose that the cold spot could be linked to variations in dark energy density. Dark energy, the mysterious force driving the acceleration of the universe's expansion, might not be evenly distributed. If certain regions have higher or lower densities, they could create localized effects on space-time, altering the behavior of photons passing through them. This idea connects the cold spot to one of the universe's biggest unanswered questions. What exactly is dark energy, and how does it behave? Cosmological strings are an additional fascinating idea. It is believed that these fictitious space-time flaws originated in the early cosmos. Temperature anisotropies might be generated by a string that distorts the space-time continuum if it is located close to the cold spot. Although cosmic strings have not been detected in the physical sense, they are a strong contender due to the fact that their theoretical characteristics match with certain cold spot characteristics. What can be ruled out is contamination from our galaxy. Careful studies have shown that neither galactic dust nor other foreground sources account for the anomaly. This strengthens the case for its cosmic origins, leaving little room for mundane explanations. Still, its precise distance of 1.8 billion light-years adds a layer of uncertainty, as galaxy surveys used to map this region rely on assumptions that are not yet universally confirmed. The alignment of the cold spot with the universe's CMB dipole, the variation in temperature caused by our movement relative to the CMB, raises another question. Could there be a deeper connection between the cold spot and the motion of local structures, like galaxy clusters? If so, it might point to an unexpected link between local and large-scale phenomena, blurring the lines between cosmic distances. Some argue that the cold spot isn't a void at all, but rather an overdense region that paradoxically appears colder due to suppressed energy transfer during the reionization era. In this scenario, early structures in the universe could have interacted with photons differently, creating a signature that mimics a void. This idea ties the cold spot to the earliest epochs of structure formation, offering a rare glimpse into the chaotic beginnings of galaxy and cluster formation. The limits of the cold spot are yet another mystery. In contrast to other temperature differences over the CMB, which exhibit more smooth transitions, its edges are very sharp. This sudden shift might be the result of a confined structure or event, such a cosmic webhole. Our present knowledge of the distribution of matter and energy on the biggest scales is challenged if this is so. Theories about the cold spot's origins also intersect with the physics of inflation. If inflationary energy fluctuated unevenly, certain regions might expand at slightly different rates, leaving behind temperature variations like the cold spot. These variations could even hint at different inflationary fields operating simultaneously, a possibility that complicates the simplest models of cosmic inflation. Some studies suggest that the cold spot might be a relic of primordial magnetism. Magnetic fields from the early universe, if strong enough, could suppress matter distribution in certain areas, leading to regions like the cold spot. While direct evidence for such fields is scarce, their existence would add another layer of complexity to the forces shaping the cosmos. Some have even suggested that exotic particles like axions may be at blame. The existence of these particles raises the possibility that photons undergo tiny interactions that change the energy of the photons as they travel through certain areas. This interaction might be studied in the cold spot, which could provide a unique opportunity to test ideas of particle physics that go beyond the standard model. There are some who think the cold spot could be a sign of energy escaping from the quantum vacuum. This is related to the field of vacuum energy fluctuations, which postulates that localized impacts on spacetime can be produced by transient variations in energy density. If verified, it would shed light on a hitherto unknown level of quantum dynamics that is reshaping the cosmos on a grand scale. Surveys of galaxies near the cold spot reveal unusual clustering patterns. Unlike other regions, galaxies here are sparsely distributed, supporting the supervoid hypothesis. However, the void size and effect seem disproportionate, leading some to question whether multiple smaller voids might align to create the same signature. It seems that the movement of surrounding galaxies is likewise affected by the cold spot. The gravitational pull of the cold spot may be associated with anisotropic motions, in which galaxies exhibit directional preferences. Since this might affect structures well beyond its local area, it begs the issue of how far-reaching its effect could be. Simulations of the cold spot suggest it is an incredibly rare event. In computer models, temperature variations of this magnitude occur only under specific conditions, making it statistically unlikely to be a random fluctuation. This rarity points to an underlying cause that may involve new physics or phenomena yet to be discovered. Photons passing through the cold spot carry subtle clues about its nature. Their polarization patterns, when analyzed in detail, might reveal interactions with hidden structures or fields within the region. These polarization studies are ongoing, offering hope for more concrete answers. The cold spot, according to some scientists, is an ancient vacuum that has never changed throughout the universe. This would mean that it is an immaculate artifact from the early universe, frozen in time just after the Big Bang. Therefore, learning about it might shed light on the early cosmos in a straightforward way. The gravitational potential of the cold spot might also create time delays for photons passing through it. By measuring these delays, astronomers could infer the distribution of matter within the region, offering another angle to understand its structure. Extra hints might be provided by nearby massive quasar clusters. There may be a link between the anomaly and early quasar activity if their grouping patterns coincide with the cold spot. This could connect the energy processes happening during the initial quasar ignitions to the cold spot. Transitional brown dwarfs in neighboring galactic systems. The cold spot in the cosmic microwave background is a mystery that takes us further into formation, structure, and cosmic equilibrium problems. A fresh piece of the jigsaw is the presence of transitional brown dwarfs outside of our Milky Way. These celestial bodies occupy a space in between star and planet classifications, being neither large enough to support hydrogen fusion nor tiny enough to be considered planets. They provide a unique opportunity to study the formation and evolution of these mysterious objects in environments quite different from our own, thanks to their presence in nearby galaxies. The Magellanic Clouds, brown dwarfs present unexpected characteristics. Their atmospheres, cooler than most known counterparts, suggest advanced cooling stages or unique atmospheric compositions shaped by different environmental pressures. Unlike the Milky Way, these galaxies often have lower metallicity, meaning fewer heavy elements were available when these objects formed. Yet brown dwarfs still arise, challenging the idea that higher metallicity is essential for their formation. Even more extreme boundary pushing is occurring in these nearby systems, with free-floating brown dwarfs. These objects float across interstellar space, unattached from their host stars, and provide evidence for the possibility of autonomous substellar object formation. There is conflicting evidence on how these brown dwarfs developed. Some research points to turbulent formation stages as a possible explanation, while other research suggests that they formed in low-density areas directly, avoiding the star phase completely. The unique clustering of these objects in certain regions adds to the mystery. In dwarf galaxies with active star-forming regions, brown dwarfs seem to gather near newly formed stars. This pattern may reflect the gravitational dynamics of smaller galaxies, where material is distributed unevenly, allowing substellar objects to congregate in pockets of higher density. We learn even more surprising things about these brown dwarfs from their magnetic fields. From what we can tell, the magnetic fields of nearby transitional brown dwarfs are greater than what one would predict from objects of their size and temperature. Atmospheric fields like this alter local chemistry and fast rotation speeds, which can lead to bizarre weather patterns like huge methane and ammonia storms. Rotation rates also set these objects apart. Many transitional brown dwarfs in external galaxies rotate faster than their counterparts in the Milky Way. This raises questions about how angular momentum is transferred or conserved during their formation. Faster rotation could mean less loss of energy during their early years, or it could indicate unique formation pathways influenced by their host galaxy's dynamics. The possibility that transitional brown dwarfs house exoplanets is one of the most fascinating features of these stars. Contrary to popular belief, brown dwarfs may indeed host their own planetary systems, particularly in nearby galaxies with extremely diverse environments. Mini-planetary systems unheard of in star systems may be born from remnants in the accretion disk of a brown dwarf star. Some brown dwarfs exhibit spectral lines that deviate from those seen in the Milky Way. These anomalies may result from different elemental abundances in their atmospheres, reflecting the chemical fingerprints of their host galaxies. For instance, a brown dwarf in a metal-poor galaxy might show enhanced signatures of lighter elements, offering insights into how chemistry shapes atmospheric behavior in these transitional objects. In the outer regions of nearby galaxies, brown dwarfs are found in places where star formation is thought to be less active. These discoveries challenge the idea that dense, high-pressure environments are necessary for their formation. Instead, they suggest that even in the quieter outskirts of galaxies, material can coalesce under the right conditions to create these enigmatic objects. Galactic winds in starburst regions may play a role in shaping brown dwarfs as well. These winds, driven by intense star formation, could strip or redistribute material around young brown dwarfs, influencing their mass and atmospheric composition. Studying brown dwarfs in these environments provides a rare chance to observe the effects of such extreme forces on substellar objects. Infrared studies have revealed unexpected luminosity levels in many brown dwarfs in neighboring galaxies. Some emit more infrared light than predicted, possibly due to unresolved companions or exotic processes in their atmospheres. These observations raise questions about how accurately we understand the energy dynamics of these objects, especially under conditions different from our own galaxy. From time to time, brown dwarfs can be seen in binary systems, in orbit around stars, or even as itself. These systems provide a window into complicated gravitational interactions in nearby galaxies. The formation and stability of brown dwarf orbits around other objects in these systems is still a mystery, particularly in settings where the forces of gravity are likely to be very different from our own Milky Way. An additional aspect to their investigation is the presence of brown dwarfs in tidal torrents between galaxies. Material is transported across great distances by these streams, which are created as a result of interactions between galaxies' gravitational pull. The presence of brown dwarfs in these streams provides more evidence that substellar objects are able to endure and perhaps traverse the harsh conditions of intergalactic space. The boundary between substellar objects and large exoplanets is blurred by extremely cold brown dwarfs in nearby galaxies. Their atmospheres are similar to gas giants, but their mass puts them squarely in the brown dwarf category. The need of improving our classification schemes for such objects is emphasized by these results, especially when studying them in different galactic contexts. Indicators of early galactic development can be found in certain transitional brown dwarfs. Their features provide a window into the host galaxy's star formation history by preserving details about the formation environment. A brown dwarf in a distant galaxy, for instance, may be able to bridge the gap between the present and the past by preserving chemical process fingerprints dating back billions of years. Microlensing events in neighboring galaxies have identified brown dwarfs acting as gravitational lenses. These events not only confirm the existence of these objects, but also provide precise measurements of their mass and distribution. By observing how light bends around these brown dwarfs, scientists can better understand their physical properties and their role in the broader galactic environment. In some cases, brown dwarfs appear in regions where galactic winds are most intense. These winds, often driven by massive star formation, interact with the atmospheres of young brown dwarfs, stripping away lighter elements and potentially altering their chemical makeup. Such interactions offer a rare look at how galactic-scale processes affect objects on much smaller scales. Faint accretion disks are occasionally observed in brown dwarfs in distant galaxies, which begs the interesting issue of how matter collects around things that do not undergo nuclear fusion. The systems around these objects in transition may become more intricate, since these disks might supply the building blocks for planets, moons, or even rings. Comparing brown dwarf populations across different galaxies reveals surprising variability. In some galaxies, they are relatively common, while in others, they are rare. This suggests that the conditions needed for their formation, such as gas density, metallicity, and star formation rates, vary widely between galaxies, influencing their frequency and distribution. The upcoming James Webb Space Telescope and other future investigations will undoubtedly change the way we perceive transitioning brown dwarfs. We want to find out how they formed, how they evolved, and what function they play in nearby galaxies by studying their atmospheres in unprecedented detail. As a result of these findings, our knowledge of these objects and how they fit into the cosmos will expand. Microlensing events near the galactic halo. What lies beyond the studied transitional brown dwarfs in nearby galaxies is frequently much more concealed, yet it brings us to the periphery of known star formation processes. In the vicinity of the Milky Way's halo, microlensing events unveil a domain where invisible entities subtly mold the cosmos through gravitational forces. These occurrences take place when a large celestial body acts as a natural lens, bending and magnifying the light from a faraway star. One distinctive feature of microlensing in the galactic halo is its ability to reveal objects that would otherwise remain unseen. The halo's vast and sparsely populated region is often detected through microlensing. These planets drift unattached to any star, their faint existence betrayed only by the gravitational pull they exert on light. Unlike the planets we know, these rogues are loners, flung into interstellar space by chaotic interactions in their parent systems. Each detection adds to a growing census of these free-floating worlds, suggesting they might be more common than once thought. Beyond planets, microlensing events near the halo have also pointed to the presence of compact objects that might be linked to dark matter. MACHOs, massive compact halo objects, are one such candidate. They include white dwarfs, neutron stars, and possibly even primordial black holes, all of which could explain some of the dark matter thought to dominate the universe. While not all microlensing detections align with this theory, the possibility remains intriguing, especially when these events deviate from expected patterns. The halo's dynamics bring high velocities into play. Many objects detected here are moving faster than stars in the galactic disk, hinting at origins tied to ancient galactic collisions or intergalactic migrations. These high-velocity lenses not only magnify light, but also alter its timing, introducing delays that give astronomers clues about the lensing object's speed and mass. These delays, though small, reveal the subtle dance of gravity at the halo's edge. Microlensing events reveal these substellar objects, which are frequently too weak to be seen directly. Brown dwarfs may be more common in less dense parts of the galaxy than previously believed, according to their halo presence. The halo offers a low-pressure, low-metallicity environment apart from the galactic plane, which poses a challenge to beliefs on the formation of such objects. The presence of weak dwarf galaxies has also been probed via microlensing near the halo. The gravitational pull of these dwarf black galaxies causes the light from stars in the background to be bent every so often as they circle the Milky Way like satellites. Microlensing helps to trace the distribution and importance of these galaxies in galactic development by revealing their hidden mass, which is otherwise undetectable to standard telescopes. Interstellar dust within the halo has been studied through these events as well. As light from distant stars passes through the halo, it interacts with dust clouds, altering its color and brightness. These changes, detected during microlensing, offer insights into the composition and spread of interstellar dust beyond the galactic core. Understanding this distribution helps refine models of how matter moves within the galaxy, especially in regions far removed from active star formation. Occasionally, microlensing detects exoplanets orbiting stars in the halo. These planets, unlike those around Sun-like stars in the galactic disk, exist in systems shaped by different histories. They might orbit older stars or exist in regions with lower metallicity, offering a chance to study planetary formation under alternative conditions. Each detection provides a rare glimpse into the diversity of planetary systems across the galaxy. In certain cases, halo microlensing events display aberrant light curves, which might indicate the existence of binary systems or possibly several lenses running parallel to each other. To solve these intricate occurrences, which are like jigsaw puzzles, one must dissect the impacts of each lensing item. Binary systems, in which two compact objects, such as neutron stars or white dwarfs, circle one another, are occasionally revealed by the anomalies. The technique has even detected microlensing of background quasars, massive sources of light located billions of light-years away. When a halo object acts as the lens, it magnifies the quasar's light, offering insights into both the lensing object and the distant quasar. These rare events highlight the halo's role as a natural laboratory for studying both nearby and far-off phenomena. The presence of two dim remains, such as neutron stars or black holes, has been suggested by certain microlensing occurrences to be indicative of dark binary systems. These systems, which are not detectable using conventional methods, contribute to the mounting evidence of a concealed population of star remnants in the halo. With each new finding, our knowledge of stellar evolution and the materials they leave behind is expanded. Halo microlensing also bridges the gap between galaxies. For example, the Andromeda galaxy is often the backdrop for these events, with its stars providing the light sources. As lensing objects in the Milky Way's halo bend Andromeda's starlight, they create opportunities to study both galaxies simultaneously. This interaction between two massive structures demonstrates the interconnectedness of cosmic systems, even at vast distances. Some of the most fascinating discoveries involve microlensing by primordial black holes, thought to be remnants from the early universe. These black holes, if they exist, would be small and nearly impossible to detect directly. However, their gravitational effects during microlensing events could reveal their presence, offering a direct link to conditions just after the Big Bang. While evidence remains scarce, the search continues, with each potential event sparking new interest. The halo also harbors substructures, small-scale clumps of matter that contribute to microlensing event rates. These substructures, possibly composed of dark matter, create variations in how light bends, offering a glimpse into the finer details of the galaxy's mass distribution. Studying these effects refines our models of the Milky Way's halo and its role in the larger cosmic web. Time delays in halo microlensing events add another layer of information. As light from a background star passes through multiple gravitational wells, its arrival time is shifted slightly. Measuring these delays allows astronomers to estimate the lensing object's mass and velocity, providing a clearer picture of the halo's hidden population. Some microlensing observations point to the existence of extragalactic nomads, or objects that have been expelled from their home galaxies and are now free to travel the cosmos. Galaxies' chaotic processes have formed a population of cosmic nomads, which includes stars, planets, and maybe brown dwarfs. Microlensing events near the halo have even been linked to the detection of tidal streams, the remnants of smaller galaxies torn apart by the Milky Way's gravity. These streams often contain stars and other compact objects, their gravitational influence detectable during microlensing. Mapping these streams helps reconstruct the history of galactic mergers and interactions. Microlensing measures are becoming more precise with each passing year because of technological advancements. More information on the invisible parts of our galaxy will be revealed in future surveys using powerful telescopes, which will give even finer details regarding the masses and distributions of halo objects. As time goes on, the halo reveals itself to be less of a mystery and more of a fertile ground for exploration, bridging the gap between ourselves and the invisible forces molding the universe. Cepheid variable stars. We are able to glimpse previously undiscovered objects thanks to gravitational lensing events in the Milky Way's halo, which further demonstrates how interdependent everything is in the universe. However, another potent instrument for cosmic knowledge is revealed when we shift our attention to Cepheid variable stars. Because of their regular pulsations, these stars are now indispensable for calculating astronomically large distances. A Cepheid variable star is an accurate, standard candle for measuring the size of the universe, since its brilliance is exactly related to its pulsation cycle. Unlike most stars, Cepheids change their brightness over days or weeks. This regular rhythm isn't random. It's driven by a process involving ionized helium in their outer layers. As the helium heats, it expands, causing the star to brighten. When the helium cools, the star contracts, dimming again. The timing of these changes tells us how luminous the star is. Comparing this intrinsic brightness to what we observe reveals its distance. The rich variety of habitats in which Cepheids thrive is one of their greatest assets. These stars provide light on areas that would otherwise be obscured by material floating across space, spanning from dwarf galaxies to the Milky Way and beyond. Seeing them in infrared light allows us to see farther into the distance because it cuts through this haze. When trying to map galaxies concealed by dense gas and dust clouds, this skill really shines. The role of Cepheids isn't confined to the Milky Way. Their discovery in the Andromeda galaxy by Edwin Hubble was pivotal. It revealed that Andromeda was not a nebula within the Milky Way, as once thought, but a galaxy in its own right. This finding expanded our understanding of the universe's true size and diversity. Today, Cepheids remain crucial for measuring distances to galaxies far beyond our local group. These stars are also invaluable for understanding the structure of our own galaxy. Their distribution helps trace the Milky Way's spiral arms, revealing the galaxy's overall shape and size. By combining Cepheid measurements with other tools, astronomers have created detailed 3D maps, showing how stars and matter are distributed across the galactic disk. In starburst galaxies, where intense star formation is taking place, Cepheids offer a way to measure distances and study regions of active stellar birth. These environments are challenging to observe due to their brightness and complexity. But Cepheids act as anchors, providing consistent reference points in chaotic systems. Their presence in these galaxies helps refine models of how stars form and evolve under extreme conditions. Additionally, Cepheids allow us to measure distances both inside and beyond the Milky Way. Another type of standard candles, type Ia supernovae, have their brightness calibrated by them. This connection allows us to examine the expansion of the universe by extending our reach to galaxies that are millions or perhaps billions of light-years away. Recent disagreements on the Hubble constant, the rate of cosmic expansion, have resulted from inconsistencies between measurements taken with the Cepheid and other techniques. While Cepheids are known for their brightness patterns, recent studies reveal complexities. Variations in metallicity, or the amount of heavy elements in a star, can subtly alter their luminosity. This requires astronomers to adjust their calculations when observing Cepheids in metal-rich or metal-poor environments. Understanding these effects ensures that their role as standard candles remains accurate, even across diverse galactic systems. Many Cepheids are found in binary systems, complicating their observed light curves. The gravitational pull of a companion star can influence a Cepheid's pulsation or brightness. Correcting for these interactions adds another layer of precision to distance measurements. In some cases, these binaries provide opportunities to study the mass and dynamics of both stars, enriching our understanding of stellar evolution. Furthermore, Cepheids help show how stars and galaxies move. In addition to mapping distances, we can learn more about the rotation and interaction of galaxies from their positions and velocities. Scientists can learn about the effects of gravity on Cepheid structure by examining them in neighboring galaxies and following their motions. In star clusters, Cepheids also indicate the passing of time. It is possible to deduce the age and history of a cluster of galaxies by measuring the ages of its individual Cepheid stars. Stars develop in groups over billions of years, and this gives us a peek inside that process. The Cepheids are leftovers of previous galactic mergers that identify the locations in the Milky Way's halo where our galaxy and others have collided. The connection between Cepheids and their environments extends to the study of interstellar dust. As Cepheid light passes through dust, it changes in brightness and color. By analyzing these changes, astronomers gain insights into the composition and distribution of dust in galaxies. This information helps refine distance measurements and reveals the conditions under which stars and planets form. Some Cepheids exhibit unusual behavior. A subset shows extreme pulsation amplitudes, challenging existing models of stellar dynamics. These outliers offer opportunities to explore less understood processes, such as how energy moves within a star's layers. Others show variable periods, suggesting they are evolving rapidly, crossing the Cepheid instability strip multiple times during their lifetimes. The instability strip itself is a narrow band on the Hertzsprung-Russell diagram, where stars transition into Cepheids. Its boundaries depend on temperature and luminosity, providing a natural laboratory for studying stellar interiors. Observing stars entering or leaving this strip offers clues about how helium fusion drives their pulsations. Cepheids in polar ring galaxies, rare systems with rings of stars orbiting perpendicularly to the galaxy's plane, have provided unique distance measurements. Their presence in these unusual structures highlights the adaptability of Cepheid studies to diverse environments. Similarly, observing Cepheids in faint dwarf galaxies has expanded our understanding of these smaller systems and their role in the broader cosmic web. Recent advancements, such as data from the Gaia spacecraft, have improved Cepheid parallax measurements, enhancing our understanding of their intrinsic properties. These precise measurements refine the cosmic distance ladder, making Cepheids even more reliable for mapping the universe. High-latitude molecular clouds beyond the Milky Way's core. The precision of Cepheid variable stars in mapping cosmic distances highlights how light itself can serve as a guide to understanding the universe's structure. Shifting focus from stars to interstellar matter, high-latitude molecular clouds offer a contrasting glimpse into the building blocks of the galaxy. Located far from the Milky Way's bustling core, these clouds are isolated pockets of cold gas and dust, quiet yet rich with clues about the galaxy's outskirts. These clouds are among the coldest places in the galaxy, where molecular hydrogen exists near absolute zero. Such low temperatures allow unique chemical processes to unfold, forming molecules that cannot survive in warmer, more energetic environments closer to the core. Organic compounds like methanol and formaldehyde are frequently detected, hinting at the potential for complex chemistry, even in these sparse regions. Unlike the molecular clouds that populate the galaxy's spiral arms, high-latitude clouds often lack the bright, active star-forming regions seen in more central areas. This dormancy suggests they represent an earlier stage of evolution, or perhaps they have been left undisturbed for millions of years. Despite this inactivity, they hold vast reserves of material that could someday ignite star formation if external forces, like galactic winds or collisions, compress them enough. Their positions far above or below the galactic plane raise questions about their origins. Some appear to be remnants of past violent events, such as supernova explosions that ejected gas from the disk. Others might represent material slowly accreting back into the galaxy from the halo. These motions are often irregular, with velocities that defy the patterns of galactic rotation, hinting at interactions with unseen forces or structures. Some high-latitude molecular clouds are positioned near the edges of the Fermi bubbles, massive outflows of gas extending above and below the galactic center. These clouds may have been shaped by interactions with these energetic outflows, their edges compressed or eroded by the force of material ejected from the core millions of years ago. Their proximity offers a way to study how such large-scale phenomena impact smaller structures in the galaxy. The presence of interstellar dust within these clouds further heightens the mystery. Grainy dust protects molecules from the sun's rays, making them ideal environments for chemical processes. Astronomers learn about star formation and evolution and galactic material distribution by analyzing the makeup of these grains. These granules are involved in the interstellar medium's chemistry and also function as transporters of stuff. The isolation of high-latitude clouds makes them ideal for studying the effects of cosmic rays, high-energy particles that permeate the galaxy. In denser regions, these rays are absorbed or scattered, but in the sparse environments of the galactic outskirts, their effects are more pronounced. They influence chemical reaction rates, leading to unique molecular signatures that differ from those found in more central regions. Observations suggest that some of these clouds may act as bridges between the galaxy and the intergalactic medium. They share similarities with gas streams seen flowing into the Milky Way from its surroundings, raising the possibility that some high-latitude clouds could have extragalactic origins. This connection blurs the line between galactic and intergalactic material, emphasizing the dynamic exchange of matter on cosmic scales. These clouds also offer a window into the galaxy's metallicity, or the abundance of heavy elements. Their chemical makeup reflects the history of star formation in the galaxy, revealing how metals produced in earlier generations of stars have been distributed over time. By comparing clouds at different latitudes, astronomers can trace the chemical enrichment of the Milky Way across vast distances. Dark molecular gas, a component of these clouds that remains undetectable in traditional CO surveys, provides further evidence of their hidden complexity. Alternative methods, like gamma-ray emissions, have revealed significant reservoirs of this dark gas, challenging assumptions about the completeness of molecular cloud studies. This dark component hints at processes that are still poorly understood, even in these well-studied regions. Clues regarding the galaxy's vertical motion seem to be held by a few clouds at high latitudes. Their current locations and speeds point to a possible ejection from the disk as a result of previous encounters or starbursts. Another possibility is that they stand for gas slowly re-entering the plane, which would make them cosmic recycled material that has been around for a very long time. The lack of active star formation in these clouds doesn't mean they lack potential. Many of them hold enough cold gas to ignite star formation if disturbed. A passing shockwave or gravitational interaction could compress these clouds, transforming them into stellar nurseries. Observing such transitions in real time would offer rare insights into how stars emerge from quiescent gas. These clouds undergo interactions along the boundary between the galactic halo and its periphery, the details of which are still a mystery. The outer layers may be eroded by the hot halo gas, but the denser, colder cores would stay put. Because of this interaction, complicated borders are formed at which matter is transferred, which affects the disks and the halo's structure and evolution. Their motion and alignment often suggest connections to ancient galactic collisions. Some clouds may be remnants of tidal interactions with dwarf galaxies, streams of material pulled into the Milky Way during past mergers. These clues offer a way to reconstruct the galaxy's dynamic history, linking the present distribution of gas to events that occurred millions or billions of years ago. High-latitude molecular clouds also hold potential for detecting primordial molecules, like hydrogen deuteride, HD, which formed in the early universe. Their isolated environments make it easier to distinguish these ancient molecules from those produced in more recent stellar processes, providing a glimpse into conditions shortly after the Big Bang. Infrared observations have been crucial for uncovering hidden structures within these clouds. Dust and gas that remain invisible in optical wavelengths glow brightly in the infrared, revealing intricate details about their composition and internal dynamics. These observations complement studies of nearby molecular clouds, extending our understanding of these structures to the galaxy's edges. The chemistry within these clouds may offer parallels to conditions in other galaxies, particularly low-mass systems where star formation is less intense. By comparing molecular clouds across different galactic environments, astronomers can refine models of how interstellar matter behaves under varying conditions. High-latitude molecular clouds may seem like quiet outposts in the galaxy's periphery, but they hold answers to questions about the origins, composition, and evolution of the Milky Way. Their isolation and simplicity make them ideal subjects for unraveling the fundamental processes that shape the interstellar medium. Gravitational anomalies in the local void. The study of high-latitude molecular clouds gives us a closer look at how material behaves in isolation at the edges of our galaxy. Shifting the focus even farther into cosmic emptiness, the local void presents one of the universe's most puzzling regions. This vast, empty expanse stretches roughly 150 million light-years and sits near our own Milky Way. Unlike the dense web of galaxies that form the cosmic filaments, the local void is a desert in the sea of cosmic matter, a place where gravitational forces are strikingly weak. The local void isn't just a space devoid of galaxies. It is also an area where the rules of gravity behave differently. With so little mass to exert gravitational pull, objects near the void appear to accelerate outward. This phenomenon, sometimes called void repulsion, isn't due to any direct force, but rather the absence of significant gravitational binding within the void. The Milky Way and its neighbors in the Laniakea supercluster are subtly nudged away from this void, adding to the dynamic flow of galaxies within the cosmic web. Matter gathers as filaments and clusters around the margins of the local void, which are bounded by thick galaxy walls. Boundaries like this separate regions dense with galaxies from the empty space. Disparities in the distribution of matter across the cosmos are shown by the striking difference between these zones. Astronomers have gained a better understanding of the cosmic web's structure and evolution by seeing this difference. The void's origins trace back to the early universe, where primordial fluctuations in matter density led to some regions being overpopulated and others underpopulated. The local void is a modern relic of these early density gaps. As matter clumped together to form galaxies and filaments, regions like the local void were left behind, expanding more rapidly due to the lack of gravitational forces to counteract the universe's overall expansion. One of the most noticeable characteristics of the local void is its absence of gravitational effect. Local galaxies are traveling at unusual speeds, not following the standard models of cosmic expansion. The shape and bounds of the local emptiness have been mapped by these motions, and instead of a perfectly round emptiness, scientists have found an uneven structure. Here, the cosmic terrain is shaped by the movement of matter and energy, and its irregularity implies complicated interactions with the surrounding galaxy walls and filaments. Despite its emptiness, the local void isn't entirely devoid of matter. Sparse clouds of gas and dust may drift through its vast interior, remnants of material that never coalesced into stars or galaxies. Some of these clouds may even contain low metallicity gas, preserved since the early universe. This pristine material offers clues about conditions in the universe shortly after the Big Bang, untouched by the chemical enrichment processes of stars. The local void may also harbor rogue planets, brown dwarfs, or even black holes, objects ejected from neighboring galaxies or formed in isolation. These unseen wanderers contribute little to the void's gravitational pull, but serve as a reminder that even the emptiest regions of the universe are not entirely barren. The weak gravitational forces within the void have implications for light traveling through it. Photons from distant galaxies and the cosmic microwave background, CMB, pass through the local void with minimal lensing or distortion. This lack of interaction creates a gravitational cold spot, where light retains its original trajectory and properties, making the void an ideal region for studying light's behavior in the absence of strong gravitational fields. Studying the local void also challenges current cosmological theories. Its size and emptiness raise questions about how voids form and evolve. Some theories suggest that voids like this could amplify the effects of dark energy, the mysterious force driving the universe's accelerated expansion. With so little mass to counteract it, dark energy may dominate in the local void, causing it to expand more rapidly than denser regions. Due to its relative lack of matter, the local void is an ideal environment in which to test competing theories of gravity. Various theories, including modified Newtonian dynamics, MOND, suggest that gravitational forces act differently in low-density settings. The movement and interaction of galaxies near the edge of the vacuum may be studied to test these hypotheses. At the intersection of the void and its surrounding galaxy walls, gas streams may cross the boundaries, linking the emptiness with the dense structures around it. These intergalactic streams transport material across cosmic distances, redistributing matter and influencing galaxy formation along the void's edges. The movement of these streams offers a glimpse into the dynamic processes that shape the universe on the largest scales. Interestingly, the void's emptiness doesn't mean complete stillness. The lack of mass and gravitational damping may accelerate interactions along its boundaries, leading to more frequent mergers and collisions among galaxies near the void. These interactions can produce tidal forces that elongate galaxies, shaping their structure and motion. What may be beneath the void's apparent substructures is another unknown. Detailed scans indicate that the local void may contain microscopic clumps of matter that never fully coalesced into galaxies, despite its empty appearance at first inspection. Information on the early cosmos and the evolution of underdense areas may be gleaned from these substructures. The void's role extends beyond the boundaries of our own galaxy. It provides insights into the larger scale alignment of voids and filaments across the universe. The local void's orientation relative to other cosmic voids may reveal patterns in the universe's structure, challenging assumptions about isotropy, the idea that the universe looks the same in all directions. The local void also intersects with broader questions about the universe's composition. The absence of significant dark matter within the void may suggest variations in how dark matter clustered during the early stages of cosmic formation. These variations could help refine models of dark matter's behavior and its interactions with visible matter. Observations of galaxies at the void's edges reveal unusual rotation curves, likely influenced by the reduced gravitational pull from surrounding regions. These anomalies provide additional opportunities to test the distribution and properties of dark matter near the void. Some theories even link voids like the local void to multiverse hypotheses, suggesting that their emptiness could result from interactions between our universe and neighboring ones. While speculative, these ideas highlight how voids challenge conventional models and inspire new approaches to understanding the cosmos. As a last point, the enormity and relative loneliness of the local void highlight the variety of the cosmos. Every part of the cosmos, from the thickest galaxy centers to the darkest cosmic gaps, reveals something new about the processes and forces that mold our reality. Rather than being a static empty space, the local void is an intricate and ever-changing feature that bridges the gap between the familiar and the unfamiliar, the full and the empty, the apparent and the hidden. Gamma-ray halos around active galactic nuclei, beyond the Milky Way. The gravitational anomalies of the local void reveal the delicate balance of forces that shape the universe. Moving further outward, the gamma-ray halos surrounding active galactic nuclei, AGN, open a window into the most energetic regions beyond our galaxy. These halos are not just luminous features, they are intricate markers of immense cosmic energy, tracing how it disperses far beyond the bounds of individual galaxies. AGN, powered by supermassive black holes, generate jets of material moving at nearly the speed of light. The gamma-ray halos surrounding them extend far beyond the visible boundaries of their host galaxies, interacting with the intergalactic medium. This interaction, driven by high-energy photons, creates a cascade effect. As these photons collide with particles in the intergalactic medium, secondary particles are formed, spreading energy across vast regions and creating the glowing halos we observe. One striking feature of these halos is their size. They stretch for hundreds of thousands of light years, often overshadowing the galaxies they originate from. This extensive reach suggests that the energy emitted by AGN jets influences not just their immediate surroundings, but also the larger cosmic environment. By studying these halos, scientists uncover how AGN feedback mechanisms shape galaxy evolution and the dynamics of the intergalactic medium. In a way, the halos are like a cosmic magnetic field map. The gamma rays emitted by AGNs are bent and scattered by interfering magnetic fields, which causes the halos to lengthen as they pass across space. Scientists can deduce the intensity and direction of intergalactic magnetic fields by studying the structure and size of these halos. Despite their relative weakness, these fields are essential in controlling the flow of energy and matter across the cosmos. Gamma-ray halos also shed light on the properties of the intergalactic medium. The density and composition of this medium affect how gamma rays propagate. For instance, the interaction of gamma rays with cosmic microwave background (CMB) photons creates new particles, extending the halos further. These interactions depend on the energy levels of the gamma rays and the conditions of the medium they travel through, offering insights into the large-scale structure of the universe. The presence of gamma-ray halos around AGN is also tied to ultra-high energy cosmic rays. AGN jets are among the few sources in the universe capable of accelerating particles to such extreme energies. When these cosmic rays collide with the intergalactic medium, they produce secondary gamma rays, contributing to the halo's luminosity. This connection between gamma-ray halos and cosmic rays helps trace the origins and paths of these elusive particles. Not all AGN produce halos of the same intensity or size. Variations depend on the AGN's type, the properties of its jets, and the surrounding environment. Blazars, a subset of AGN where the jets point directly towards Earth, exhibit particularly bright gamma-ray halos. Their alignment amplifies their luminosity, making them prime candidates for studying the relationship between AGN activity and gamma-ray emissions. In some cases, gamma-ray halos reveal the presence of AGN that are otherwise hidden. Dust and gas often obscure the central regions of galaxies, masking their AGN in optical and X-ray observations. Gamma rays, however, penetrate these barriers, providing a clearer view of the energetic processes at play. This ability makes gamma-ray halos a valuable tool for identifying faint or obscured AGN across cosmic distances. The interaction between AGN and their environment extends beyond the halos. Gamma-ray emissions heat the surrounding gas, altering its temperature and ionization state. This heating effect can suppress star formation in nearby regions as the gas becomes too hot to collapse into stars. In this way, AGN activity influences not only its host galaxy, but also neighboring systems, shaping the evolution of galaxy clusters and the intergalactic medium. Gamma-ray halos are not static features. As AGN evolve, their energy output changes, affecting the size and intensity of their halos. Younger AGN with active jets produce compact, bright halos, while older AGN with declining activity exhibit more diffuse, fainter structures. Observing halos across different stages of AGN evolution provides a timeline of how these powerful systems interact with their surroundings. In some galaxy clusters, gamma-ray halos from multiple AGN overlap, creating a composite glow that reveals the dynamics of the cluster environment. These overlapping halos highlight the complex interplay between AGN, their host galaxies, and the surrounding medium, providing a multi-layered view of cluster formation and evolution. The shape of gamma-ray halos can also be influenced by AGN winds. These powerful outflows, driven by the energy of the central black hole, push material outward, shaping the surrounding medium. The resulting asymmetries in the halos offer clues about the direction and intensity of these winds, as well as their role in regulating the growth of the black hole and its host galaxy. Observations of gamma-ray halos across different redshifts reveal how AGN activity and the intergalactic medium have changed over cosmic time. In the early universe, when AGN were more active, their halos were likely brighter and more widespread. By comparing halos at various distances, scientists can trace the evolution of AGN feedback and its impact on the universe's large-scale structure. Relic AGN activity can also be detected via gamma-ray halos. When the center AGN stops radiating, the halo is a faint trace of its former activity. These artifacts provide light on the past of AGN and their impact on the universe by preserving records of energy production from bygone eras. In some regions, gamma-ray halos interact with large-scale cosmic filaments, highlighting the flow of energy and matter between galaxies. These interactions underscore the interconnectedness of the universe, where no structure exists in isolation. The energy dispersed by AGN through their halos contributes to the overall dynamics of the cosmic web, influencing how galaxies and matter are distributed. By studying gamma-ray halos, scientists refine their understanding of the universe's most energetic processes. These halos are not just luminous phenomena. They are windows into the forces that shape galaxies, regulate star formation, and connect structures across cosmic scales. They extend our view beyond individual galaxies, revealing the intricate dance of energy and matter. Isolated neutron stars in extragalactic space. Isolated neutron stars in extragalactic space provide one of the most striking examples of how objects can escape the gravitational bonds of their home galaxies and exist in the vast intergalactic void. These stars, remnants of supernova explosions or the chaotic results of stellar collisions, embody extremes, extreme density, velocity, and loneliness in the great cosmic emptiness. Unlike their galactic counterparts, these neutron stars float alone, untethered to any visible system, offering a rare glimpse into the interactions between stellar remnants and the intergalactic medium. The story often begins with violent ejections. When a massive star in a binary system explodes as a supernova, the resulting neutron star can be hurled into space at incredible speeds. Some achieve velocities that not only take them out of their stellar neighborhood, but also eject them completely from their galaxy. These runaway stars, traveling at hundreds of kilometers per second, continue their solitary journeys for millions or even billions of years. Their high velocities are a testament to the asymmetric forces of their creation. The core collapse of a massive star doesn't always occur evenly. Slight asymmetries during the explosion can impart a kick strong enough to send the neutron star hurtling into space. Others may result from interactions in dense star clusters, where gravitational slingshots between massive objects catapult them out into the void. Even after ejection, these stars remain detectable, if you know where to look. Many emit faint X-rays, a result of their surface temperatures reaching hundreds of thousands of degrees. Some are detectable as pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. These emissions can be faint and intermittent, but they provide key clues to the star's rotation, magnetic field, and age. In rare instances, these isolated neutron stars may interact with the sparse intergalactic medium. As they move through this tenuous gas, they create bow shocks, regions of compressed and heated material. These shocks emit faint light that can be observed under the right conditions, highlighting the star's path through the void. Such interactions offer valuable data about the properties of the intergalactic medium, a largely invisible component of the universe. Some of these neutron stars are magnetars, with magnetic fields trillions of times stronger than Earth's. These extreme fields can cause starquakes, sudden shifts in the star's crust, that release bursts of high-energy gamma rays. Detecting such bursts from extragalactic magnetars is rare, but provides a wealth of information about their magnetic activity and the environment around them. Their status as artifacts of galactic development is an intriguing feature of neutron stars that have been isolated. During their galaxy's early phases of formation, many of these stars were expelled. One way to learn about galactic motion and interaction throughout cosmic timeframes is to look at their present locations and trajectories. As a result of being engulfed by more massive systems, dwarf galaxies may leave a trail of stars dispersed over intergalactic space. The detection of isolated neutron stars also challenges the limits of observational technology. Their faintness makes them some of the most difficult objects to study, often requiring multi-wavelength observations across radio, X-ray, and gamma-ray spectra. Each observation adds a piece to the puzzle, helping scientists identify and characterize these elusive objects. From time to time, gravitational lensing reveals solitary neutron stars. Their intense gravitational pull distorts the light emitted by objects in the background. Even neutron stars that do not generate visible light can be detected through microlensing occurrences. Not only do these findings prove the star exists, but they also reveal information on the star's mass and its speed. Some neutron stars may accrete material from the intergalactic medium, a process that can reignite activity on their surfaces. This accretion produces faint emissions, often in X-ray wavelengths, that provide insights into the star's surroundings. The presence of heavy elements in these emissions also hints at the neutron star's origin, as these elements were likely synthesized in the supernova explosion that created it. In the context of galaxy collisions, isolated neutron stars serve as markers of past interactions. When galaxies merge or pass near one another, their gravitational forces can disrupt stellar systems, ejecting stars into intergalactic space. Groups of neutron stars found in specific patterns or along the edges of such events offer clues about the timing and dynamics of these collisions. A particularly intriguing possibility is the detection of double neutron star systems in intergalactic space. These rare pairs, ejected together from their home galaxy, remain gravitationally bound and orbit one another. If they eventually merge, the resulting collision produces gravitational waves that are detectable across vast distances. Such events are prime targets for observatories like LIGO and Virgo, linking neutron star studies with gravitational wave astronomy. Fast radio bursts, FRBs, are another phenomenon potentially tied to isolated neutron stars. These mysterious millisecond-long bursts of radio waves may originate from magnetars in intergalactic space. While the exact mechanism is still unknown, the connection between neutron stars and FRBs is an active area of research, with each discovery adding to the growing body of evidence. The thermal emissions of isolated neutron stars tell a story of cooling that spans billions of years. As they radiate heat from their surfaces, they gradually fade, offering a timeline of their evolution. Comparing the temperatures and ages of multiple isolated neutron stars provides a clearer picture of how these remnants age in the cold emptiness of space. These stars create faint pulsar wind nebula, clouds of charged particles accelerated by the star's magnetic field. These nebulae can extend for light years, producing unique radiation signatures that make the neutron star's presence more apparent. Such structures are rare in intergalactic space, but offer a glimpse into the interaction between isolated neutron stars and their surroundings. We may learn more about the nature of the intergalactic medium by analyzing the patterns of star distribution, ionizing the gas and leaving behind traces of charged particles are effects of neutron stars as they go through it. We learn more about the enormous intergalactic expanses by studying these traces, which improve our predictions of the density and composition of the medium. Each isolated neutron star is a cosmic time capsule, preserving information about its origin and the events that shaped its trajectory. Their existence underscores the dynamic nature of galaxies, where even the most destructive forces, supernova explosions and collisions, can create objects that endure for billions of years. These stars, though solitary, are deeply connected to the larger story of the universe, bridging the gap between galaxies and the voids that surround them. The Fermi bubbles, expanding gas clouds at the Milky Way's edge. The story of isolated neutron stars offers a glimpse into stellar remnants that move through intergalactic space, each carrying with it the legacy of a violent ejection from its home. But the Milky Way's edges tell another tale, one written in the colossal Fermi bubbles. These structures, vast and enigmatic, extend above and below the galactic plane, providing a canvas for high-energy processes that ripple outward from the galaxy's core. The Fermi bubbles are unlike anything else in our galaxy. Spanning 50,000 light-years in diameter, they are immense clouds of gas and energy, glowing brightly in gamma rays. These emissions make them visible even against the backdrop of our bustling galaxy. The exact origins of the bubbles remain a puzzle, but most evidence points to Sagittarius A*, the supermassive black hole at the Milky Way's center. Millions of years ago, a burst of energy, perhaps a feeding frenzy, where the black hole devoured surrounding material, may have sent shock waves that carved out these structures. A different theory proposes a time of rapid star creation close to the galactic core. During such times, the gas might have been pushed outward by a combination of winds from large stars and supernova explosions, creating the bubbles. Both the black hole and starburst wind hypotheses suggest very significant and life-altering events in the galaxy's past, but the exact nature of these events is still up for discussion. The edges of the bubbles glow more intensely than their interiors. This edge brightening is caused by shock waves as the expanding bubbles collide with surrounding material. These shock waves compress and heat the gas, creating regions of higher density and energy that shine brightly in gamma rays. They also reveal details about the surrounding interstellar and circumgalactic medium, showing how the Milky Way's halo interacts with these outflows. The Fermi bubbles aren't just composed of ordinary gas. Observations suggest that they contain a mix of baryonic matter, particles like protons and neutrons, and cosmic rays, which are charged particles accelerated to nearly the speed of light. The bubbles act as a reservoir for these cosmic rays, trapping them and providing a space for studying how such high-energy particles behave in the galaxy's outskirts. The material in the bubbles isn't uniform. Enriched with heavy elements, it bears the chemical signatures of past supernova explosions and star formation events. These elements offer clues about the history of the galactic center, revealing what kinds of stars lived and died there and how their remnants were distributed. Despite their colossal size, the bubbles didn't form gradually. Evidence suggests they were created in a relatively short period, perhaps over a few million years, by an intense release of energy. This rapid formation is a striking reminder of how quickly galaxies can undergo transformative events, reshaping their surroundings almost overnight in cosmic terms. The influence of the Fermi bubbles extends far beyond their visible boundaries. As they expand, they mix with the surrounding circumgalactic medium, redistributing energy and matter on vast scales. This mixing process stirs up the gas in the halo, creating turbulence that affects the Milky Way's ability to retain or accrete material. Strangely, the gas that the bubbles come into contact with is heated as well. They stop part of the medium from cooling and condensing into new stars by injecting energy into it. It is possible that this heating effect controls the rate of star formation close to the galactic center, hence regulating the environment of the Milky Way. Radio observations of the bubbles reveal synchrotron radiation, emitted by electrons spiraling along magnetic field lines. This radiation highlights the presence of high-energy particles and offers another way to map the structure of the bubbles. Combined with gamma-ray and X-ray observations, These data provide a multi-wavelength view of the bubble's complexity. High-energy neutrinos detected near the bubbles may also originate from the processes driving their formation. These elusive particles are produced during interactions involving cosmic rays, providing yet another clue about the extreme conditions within the bubbles. As the bubbles expand, they encounter high-velocity clouds of gas near the galactic halo. These interactions leave behind imprints in the form of shocks and disturbances, revealing the bubble's impact on the surrounding environment. These encounters also highlight the interconnectedness of the galaxy, where seemingly isolated structures influence one another across great distances. Some models suggest the bubbles are remnants of relativistic jets, narrow streams of material ejected at near-light speeds. While these jets are more commonly associated with AGN, the possibility that the Milky Way once hosted similar activity raises intriguing questions about its past. Such jets would have carried enormous energy into the halo, leaving behind the expanded gas we see today. The gamma-ray emissions from the Fermi bubbles are part of a broader mystery involving excess gamma rays in the galactic center. This excess could be linked to other high-energy processes occurring near Sagittarius, a star. The bubbles offer a window into these enigmatic phenomena, providing a bridge between known and unknown forces shaping the galaxy. The bubbles' shape and size are not uniform. As they expand, they encounter regions of varying density in the interstellar medium, creating asymmetries and distortions. These irregularities provide insights into the properties of the medium itself, revealing its structure and composition. The bubbles also impact the surrounding circumgalactic medium. By redistributing gas and energy, they alter the density profile of the halo, shaping how material flows into and out of the Milky Way. This redistribution has long-term implications for the galaxy's evolution, influencing future star formation and gas accretion. Studying the Fermi bubbles isn't just about understanding our galaxy, it's also about placing the Milky Way in a broader cosmic context. Similar structures observed in other galaxies suggest that these outflows are a common feature of galactic evolution, driven by central black holes or intense star formation. The turbulence induced by the bubbles stirs the surrounding gas, creating motion that affects how material settles or moves within the halo. This turbulence may even help maintain the hot, diffuse plasma that forms the galaxy's corona, preventing it from cooling too quickly. The rapid formation of the bubbles implies a dramatic event in the galaxy's history, one that left a lasting imprint on its structure. Whether driven by black hole activity, starbursts, or a combination of both, the energy release required to create them underscores the dynamic nature of the Milky Way's core. As the bubbles expand, they carry with them the story of their origins, a story written in gamma rays, enriched gas, and turbulent motion. Their presence reminds us that even the largest structures in the galaxy are shaped by events on much smaller scales, where immense energy is unleashed, transforming everything in its path. Through their study, we uncover not just the history of our galaxy, but the processes that define galaxies across the universe. Ultra-faint dwarf galaxies as dark matter. Laboratories. The vast edges of the Milky Way, shaped by expanding Fermi bubbles and glowing with gamma rays, eventually fade into the darkness of intergalactic space. Yet even here, faint and ancient structures remain, orbiting quietly at the galaxy's fringes, ultra-faint dwarf galaxies. These ghostly remnants, nearly invisible against the cosmos, are some of the most dark matter-dominated objects ever discovered. Despite their faintness, they reveal critical clues about dark matter, the structure of the universe, and the early days of galaxy formation. Ultra-faint dwarf galaxies, or UFDs, defy expectations. With only a few thousand stars, these galaxies are incredibly dim, often outshone by individual globular clusters. Yet their gravitational pull suggests they are far more massive than their visible matter would imply. For every star visible in these galaxies, thousands of solar masses of unseen dark matter lurk in the shadows, making them ideal laboratories for studying this mysterious substance. The movements of stars within UFDs tell a clear story. Unlike brighter galaxies, where stellar motions are influenced heavily by visible matter, the stars in UFDs move under the control of dark matter. By studying these movements, Scientists map the distribution of dark matter in these galaxies, revealing dense, compact cores that hint at the properties of dark matter itself. Are these cores smooth, as standard cold dark matter theories predict, or are they influenced by self-interactions between dark matter particles? Each new observation refines our understanding. UFDs are not just rich in dark matter, they're also relics of the past. These galaxies stopped forming stars billions of years ago, preserving their early histories like cosmic fossils. Their stars are among the oldest in the universe, containing low amounts of heavy elements or metals. This low metallicity reveals that UFDs underwent only brief periods of star formation before cosmic reionization, a process that heated the intergalactic medium and stripped small galaxies of their gas, brought an abrupt halt to their growth. The chemical simplicity of these galaxies provides another advantage for researchers. Unlike more complex systems, where the chemistry has been stirred and enriched by multiple generations of star formation, UFDs maintain pristine conditions. Their stars act as time capsules, preserving information about the universe's earliest supernovae and the processes that enriched the cosmos with heavy elements. Some UFDs show signs of having been disrupted by the Milky Way's gravity. These tidal interactions stretch and distort their shapes, creating elongated structures or even streams of stars. These features reveal how galaxies evolve through interactions with larger systems and provide critical insights into the gravitational forces at work in the Milky Way's halo. The faintness of UFDs doesn't make them insignificant. On the contrary, their extreme dark matter content makes them crucial for testing theories about galaxy formation and the behavior of dark matter. Standard cosmological models predict that the Milky Way should host hundreds of UFDs, yet only a few dozen have been observed. This missing satellites problem raises questions about whether dark matter behaves differently on small scales, or if current telescopes are simply missing these faint objects. Advances in telescope technology promise to reveal more of these elusive galaxies. Instruments like the Vera Rubin Observatory will detect fainter objects than ever before, potentially uncovering the hidden population of UFDs predicted by simulations. These discoveries will not only resolve discrepancies in satellite counts, but also refine our models of how dark matter interacts with ordinary matter. Despite their low luminosity, UFDs have already played a role in dark matter detection efforts. Astronomers have used these galaxies to search for gamma rays that might indicate dark matter particle annihilation. Although no definitive signals have been detected, the lack of gamma ray emissions places constraints on the properties of dark matter, ruling out certain models while supporting others. In addition to their tiny size and closeness to the Milky Way, some UFDs include gas indications, which is an unexpected discovery. It is still unclear how these galaxies manage to keep their gas content constant despite their interactions with their surroundings. We may learn more about dark matter's function as a galactic shield if we find out the answer. Additionally, UFDs evaluate non-standard theories of gravity, including MOND. For star movements in dark matter-dominated systems, MOND predicts different behaviors than standard models. By tracking stellar motions in UFDs, we can disprove these hypotheses and find out for ourselves if dark matter is real or if galactic gravity is different. Each UFD has its own unique star formation history. Some formed a single burst of stars over 10 billion years ago, while others experienced multiple episodes of activity before becoming dormant. These histories, shaped by interactions with the Milky Way and cosmic reionization, highlight the diversity of these faint galaxies and their responses to cosmic events. The environments of UFDs also provide clues about their origins. Some appear to have formed within larger systems that were later disrupted, leaving behind these dark matter-rich cores. Others may have formed independently as some of the universe's first galaxies. Studying these systems helps reconstruct the assembly history of the Milky Way and its surrounding structures. Clusters of stars within UFDs add another layer of intrigue. These star clusters, though rare, are well preserved and serve as laboratories for studying star formation in environments dominated by dark matter. Their survival in such faint galaxies raises questions about how star clusters interact with their surroundings. and whether dark matter played a role in their formation. One possible function of UFDs in the formation of dark matter streams is the connection between the two. Since the Milky Way tidally perturbs these galaxies, their impacts on star movements may leave traces of dark matter that may be detected. The distribution of dark matter might be seen with unparalleled clarity by mapping these streams. UFDs also provide a unique perspective on how galaxies interact with the cosmic web, the large-scale structure of the universe. As these galaxies move through the web, their interactions with intergalactic gas and dark matter leave imprints that help refine models of cosmic evolution. Some UFDs are so faint that they push the limits of detection, raising the possibility that even fainter systems exist. These hyperfaint galaxies may represent the smallest and most dark matter-dominated systems in the universe, offering the purest environments for studying dark matter. The discovery of UFDs also challenges our understanding of galaxy formation. Why do some systems become massive, star-forming galaxies while others remain small and dim? The answer may lie in the interplay between dark matter, cosmic reionization, and the availability of gas. The extreme environments of UFDs make them valuable for understanding how stars form and evolve in conditions unlike those in larger galaxies. By studying these faint systems, astronomers can test how star formation operates at the limits of galactic potential. Even the absence of some elements in UFDs is noteworthy. In sharp contrast to bigger galaxies, which have core black holes in their dynamics, the majority of them do not have one. This omission raises the possibility that UFDs might not possess the necessary criteria for black hole creation. These faint galaxies are also critical for understanding the distribution of baryonic matter in the universe. As some of the most baryon-poor systems known, UFDs highlight the processes that separate ordinary matter from dark matter during galaxy formation. Ultra-faint dwarf galaxies, though faint and seemingly insignificant, hold the answers to some of the universe's biggest mysteries. By studying these dim beacons, scientists are uncovering the secrets of dark matter, the formation of galaxies, and the structure of the cosmos itself. Hyperfaint globular clusters, far beyond the galactic disk. Extragalactic winds and particles pushed far beyond the disk are shown by the high-energy borders of the Fermi bubbles, which extend outward from the center of the Milky Way. Hyperfaint globular clusters are another enigmatic object on the galaxy's periphery, much more so than these formidable formations. Dispersed like faraway whispers of the galaxy's past, these faint old clusters of stars sit far beyond the Milky Way's disk. We are challenged in our knowledge of star systems by hyperfaint globular clusters. They include some of the oldest stars ever seen, while being extremely weak and typically having fewer stars than usual clusters. The circumstances that prevailed during the early stages of galaxy formation may be inferred from these stars, which are nearly as ancient as the universe itself. The absence of heavy elements in their metallicity indicates that they originated prior to the enrichment of the interstellar medium with the components of subsequent star generations by supernovae. These clusters, despite their faint appearance, have survived billions of years. Positioned on the outskirts of the Milky Way, they have endured interactions with the galactic halo and gravitational forces that could have torn them apart. Their survival raises questions about their formation and internal structure. Hyperfaint globular clusters are not distributed randomly. Their positions trace the structure of the Milky Way's halo, the spherical region of stars, gas that surrounds the galaxy. By mapping their locations, astronomers gain a clearer picture of the Milky Way's outer regions. These clusters act as markers, revealing where the galaxy's gravitational influence fades and the intergalactic medium begins. Some hyperfaint clusters may not be native to the Milky Way. Evidence suggests that a number of these systems originated in dwarf galaxies that were later consumed by the Milky Way. Tidal interactions stripped these clusters from their parent galaxies, leaving them stranded in the galactic halo. These remnants provide a glimpse into the history of galactic mergers, showing how the Milky Way grew by devouring smaller systems. The link between star streams and certain hyperfaint clusters is an astonishing finding. These trajectories across the sky show the ways in which stars from clusters or dwarf galaxies have interacted in the past. These streams contain hyperfaint clusters, which provide a link to the processes that molded the outer halo of the Milky Way. As markers of the remains of distant galaxies, these clusters serve as directional indicators. The faintness of these clusters makes them difficult to study, but advances in telescope technology have opened new windows into their nature. The Gaia mission, with its precise measurements of star positions and motions, has been instrumental in identifying these faint systems. By studying the motions of their stars, astronomers can determine the clusters' orbits and gain insights into their interactions with the Milky Way. Despite their small size and low luminosity, hyperfaint clusters offer a wealth of information about stellar evolution. The stars in these clusters formed in isolation, with little interference from other systems. This isolation preserves the conditions of early star formation, making these clusters valuable for understanding how stars form and evolve in environments that lack the complexity of more massive systems. The chemical fingerprints of hyperfaint clusters are similarly informative. Their star's low metallicity indicates that heavy metals were scarce in the universe until supernovae filled it. Clusters with peculiar chemical abundances may have been affected by population 3 stars, the first class of supernovae. These characteristics offer unique proof of the primordial stars that molded the chemical history of the cosmos. There is new information on the missing satellites issue, thanks to the finding of hyperfaint clusters. Only a small proportion of the hundreds of weak satellites predicted by dark matter simulations have actually been found in the Milky Way. The discovery of hyperfaint clusters fills this need and raises the possibility that next-generation telescopes will find many more faint systems. Their faintness, however, is not just a challenge, it's a defining feature. Hyperfaint clusters are among the dimmest objects in the universe, pushing the limits of detection. Their discovery requires advanced techniques, such as deep imaging and careful analysis of stellar populations. Upcoming observatories, such as the Vera Rubin Observatory, are expected to uncover even fainter clusters, revealing a hidden population of these ancient systems. Some hyperfaint clusters show evidence of past interactions with high-velocity gas clouds in the galactic halo. These interactions may have stripped gas from the clusters or influenced their orbits. Understanding these interactions provides a clearer picture of the dynamic processes shaping the Milky Way's outskirts. The low stellar densities of hyperfaint clusters raise questions about their formation. How did such small, faint systems form in the early universe? Some theories suggest they are remnants of larger systems stripped down by tidal forces. Others propose they formed in isolated regions of the early universe, where conditions favored the creation of low-mass clusters. Their isolation also makes hyperfaint clusters excellent laboratories for studying stellar dynamics. Unlike dense globular clusters, where close encounters between stars are frequent, hyperfaint clusters offer a more quiescent environment. This isolation preserves the star's original orbits and provides a simpler setting for studying how stars interact with their environment. It is believed that certain hyperfaint clusters are home to extremely uncommon binary star systems. These binary systems, which evolved in low-density settings, could be different from their more large counterparts. Investigating these binary systems provides light on the formation and evolution of star pairs under harsh environments. Their faintness and simplicity make hyperfaint clusters unique markers of the cosmic web, the large-scale structure of the universe. Their positions may align with intergalactic matter flows, linking the Milky Way to larger structures. This connection highlights the role of hyperfaint clusters in understanding how galaxies and their halos interact with the broader cosmos. The discovery of hyperfaint clusters also challenges traditional models of globular cluster formation. Unlike typical globular clusters, which are dense and massive, hyperfaint clusters show that star clusters can form and survive under vastly different conditions. This diversity expands our understanding of the processes that shape star clusters across cosmic time. Hyperfaint globular clusters, despite their faintness, hold a wealth of information about the universe's past. Their stars, nearly as old as time itself, offer a glimpse into the conditions that shaped the earliest galaxies. Possible bridges of neutral hydrogen between galaxies. The vast stretches of intergalactic space may appear empty, but they are far from it. Moving beyond hyper-faint globular clusters, we encounter an even subtler phenomenon: the possible bridges of neutral hydrogen gas that link galaxies across unimaginable distances. These ethereal structures serve as silent highways, where gas flows between galaxies, fueling their evolution and providing a unique window into the dynamics of intergalactic material. Neutral hydrogen, the simplest and most abundant element in the universe, becomes visible through its emission of a specific wavelength, the 21-centimeter line. This signal allows astronomers to detect and map its presence, even in the most remote regions. When it forms bridges between galaxies, it reveals intricate interactions that cannot be seen with visible light alone. These hydrogen bridges are often the lingering evidence of past galactic encounters, showing how gravitational forces pull and stretch gas into thin, tenuous links. Some of the clearest examples of these hydrogen bridges lie in the local group, connecting familiar galaxies like the Milky Way and the Magellanic Clouds. The Magellanic Stream, a ribbon of hydrogen stretching from the Magellanic Clouds toward our galaxy, is one of the best studied cases. This stream is thought to have formed through tidal forces as the clouds passed near the Milky Way, stripping their gas into intergalactic space. Observing these structures helps scientists reconstruct the histories of these galaxies, including the timing and intensity of their interactions. But these bridges are not limited to local galaxies. In clusters of galaxies, where the density of galaxies is much higher, these hydrogen links create a complex web of connections. Some bridges are direct links between pairs of galaxies, while others form sprawling networks that trace the large-scale structure of the universe. In some cases, hydrogen bridges act as evidence of ancient mergers, long after the galaxies themselves have merged and settled into a single system. The bridges remain, slowly dissipating over time. Not all hydrogen bridges are the result of tidal forces. Some are created by the gravitational pull of unseen matter. This is particularly intriguing when bridges connect isolated galaxies far from dense clusters. The gravitational forces required to pull gas into a bridge often exceed what the visible matter in the galaxies can explain. The survival of these bridges in intergalactic space is a puzzle in itself. They exist in environments bathed in ultraviolet radiation from stars and galaxies, as well as energetic particles from cosmic rays. This radiation can ionize hydrogen, breaking it apart and making it undetectable as neutral gas. Yet many of these bridges persist for millions or even billions of years, protected by their density or the shielding effect of nearby material. Understanding this stability is key to learning how intergalactic gas behaves under extreme conditions. The motion of gas within these bridges offers further insights. By measuring the velocities of hydrogen using the Doppler effect, astronomers can map the flow of gas between galaxies. Some bridges act as inflows, channeling gas into galaxies where it fuels star formation. Others appear to be outflows, where energetic processes like supernovae or black hole activity eject gas from galaxies into intergalactic space. These flows reveal the dynamic exchanges of material that shape galaxies over cosmic timescales. Bridges connecting galaxies that are no longer interacting visually are an intriguing finding. These so-called ghost bridges indicate that even short interactions between galaxies can produce enduring traces of hydrogen. The study of these structures allows astronomers to unearth previously unseen evidence of interactions by analyzing the past. The density of hydrogen in these bridges varies widely. Some are thin, tenuous threads barely detectable, while others contain enough gas to form entire dwarf galaxies if the conditions were right. This variation provides clues about the processes that created the bridges. High-density regions may indicate recent interactions, where gas has not yet had time to spread out, while lower-density bridges may be remnants of much older events. Neutral hydrogen bridges also contribute to the cosmic web, the large-scale structure of the universe composed of galaxies and gas. These bridges often align with the filaments of the cosmic web, suggesting a connection between galactic interactions and the broader distribution of matter in the universe. By mapping these bridges, astronomers can trace how galaxies are embedded within this vast network. The discovery of hydrogen bridges has been made possible by advancements in radio astronomy. Telescopes like the Meerkat in South Africa and the Very Large Array in the United States have revolutionized our ability to detect faint hydrogen signals. Future observatories, such as the Square Kilometre Array, SKA, promise to uncover even more of these structures, extending our view deeper into intergalactic space. These bridges are not static. They evolve over time. As galaxies move apart or merge, the gas in the bridges dissipates or is reabsorbed into the galaxies. Observing this evolution provides a timeline of galactic interactions, showing how material flows change as galaxies grow and mature. Hydrogen bridges aren't just important for galaxy evolution. They might also be intergalactic medium labs. The temperature, density, and radiation characteristics within these bridges provide a one-of-a-kind setting for studying gas behavior across interstellar distances. Since these bridges may contain characteristics typical of star-forming clouds in their early stages, this has consequences for hypotheses of star formation. Some bridges exhibit signs of molecular hydrogen formation, where neutral hydrogen transitions into the denser, colder state needed for star formation. This transformation is a critical step in the life cycle of interstellar material, and observing it in bridges provides a new context for studying how stars begin to form. Theoretical models suggest that these hydrogen bridges may also play a role in transporting material between galaxies. Gas stripped from one galaxy can be funneled into another, providing a steady supply of raw material for new generations of stars. This transfer of material underscores the interconnectedness of galaxies, even across vast distances. Hydrogen bridges are difficult to analyze because of how faint they are. Their signals are too faint for the telescopes that are currently in use. Therefore, many of them go unnoticed. This shortcoming emphasizes the significance of future initiatives such as the SKA that will possess the sensitivity to discern the most subtle structures. As we uncover more about these bridges, their role in the broader context of galaxy formation becomes clearer. They are not just remnants of interactions, but active participants in the flow of material across the universe. Neutral hydrogen bridges connect galaxies in ways that extend beyond their visible boundaries. These delicate threads of gas, stretching across the void, remind us of the invisible connections that link the cosmos. They bridge not only galaxies, but also the gaps in our understanding, offering a deeper view into the complex web of interactions that shape the universe. Beyond the Milky Way's edges, they quietly weave the story. Theoretical cosmic islands, beyond galactic filaments. The vastness of interstellar space offers a stage where rogue planets drift aimlessly, unbound by the gravitational pull of any star. These solitary worlds, some of which might not be as lonely as they seem, paint a picture of cosmic chaos and interstellar interactions. Rogue planets are not just scattered randomly. In some cases, they gather in loose groups, forming enigmatic clusters. These clusters may hold the secrets to understanding planetary evolution, interstellar dynamics, and even the possibility of life in the harshest of conditions. Rogue planets likely owe their existence to violent ejections from young planetary systems. When massive celestial bodies interact in these early systems, gravitational forces can catapult smaller planets into the void. Over time, these rogue planets may find others and form clusters, bound loosely by their mutual gravitational pull. The mechanisms behind these formations are still being explored, but their existence hints at underlying connections, possibly shared origins or similar trajectories through the galaxy's gravitational fabric. The variety of rogue planet clusters is one of the most interesting things about them. These clusters contain entities of varied weights and compositions, in contrast to planetary systems that share a common gravitational anchor. There are gas giants many times larger than Jupiter among them, and there are also smaller, rocky ones. Their origins and the circumstances leading up to their eviction are cast into doubt by the diversity. Some rogue planets may have originated in molecular clouds far from any star systems on their own. Subsurface oceans could make some rogue planets unexpectedly hospitable. Without sunlight, these worlds rely on internal heat generated by radioactive decay or tidal forces from orbiting moons to maintain liquid water beneath their icy crusts. The possibility of such oceans extends the search for life beyond traditional habitable zones. These planets, despite their isolation, might harbor microbial ecosystems or chemical processes that mimic the origins of life on Earth. Observing rogue planets and their clusters is no small feat. Without a star to illuminate them, they appear as faint blips against the cosmic background. Gravitational microlensing, a method that uses the bending of light caused by a planet's mass, has been instrumental in their detection. The transient nature of these events, however, makes it challenging to identify clusters. Upcoming advancements in space telescopes promise to improve our ability to track these elusive wanderers and study their properties in greater detail. Clusters of rogue planets could also act as laboratories for studying interstellar phenomena. For example, the chemical composition of these planets might reflect the environments they've passed through, including interactions with cosmic dust and gas. These chemical signatures could provide a timeline of their interstellar journeys, revealing information about the conditions of regions far from our solar system. It's a chance to study the building blocks of planetary systems in a context entirely different from the traditional star-centric models. The dynamics within a rogue planet cluster are equally fascinating. While their gravitational bonds are weak compared to those of a star system, these bonds are enough to keep the planets loosely associated as they drift through space. Collisions within clusters, though rare, might generate heat and release material, creating temporary flashes detectable from Earth. Such events could offer glimpses into the interiors of rogue planets, providing data otherwise inaccessible. Clusters might even act as cosmic travelers, spreading material across the galaxy. Rogue planets could carry organic molecules or water, delivering these essential ingredients for life to other planetary systems they encounter. This idea links rogue planets to the broader narrative of cosmic evolution and the potential spread of life throughout the galaxy. Whether they act as catalysts for life or simply carriers of raw materials, their role in the cosmic ecosystem is worth exploring. According to theoretical models, rogue planets might potentially congregate in areas with a lot of gravitational pull, like the galactic halo. Because the halo is relatively empty, clusters may form and stay put thanks to the dominance of gravitational forces. These clusters may serve as tracers for otherwise undetectable gravitational patterns, which might shed light on the structure and dynamics of the Milky Way. The existence of rogue planet clusters also raises questions about their impact on galactic motion. As they drift, these clusters contribute to the overall mass distribution within the galaxy. Their trajectories might affect the movement of nearby stars or influence the orbits of other celestial bodies. Understanding these interactions could refine our models of galactic evolution, shedding light on how mass flows and concentrates across vast distances. Even the moons of rogue planets play a role in this story. Some rogue planets may retain their moons after ejection, forming miniature systems within interstellar space. The presence of moons introduces the possibility of tidal heating, which could sustain subsurface oceans and create unique environments for chemical activity. These rogue moon systems add another layer of complexity to the already enigmatic nature of rogue planets. Despite the challenges of detecting them, the sheer number of rogue planets suggests that they may outnumber stars in the galaxy. If true, this statistic redefines our understanding of planetary formation and the prevalence of planets in the cosmos. It also raises the possibility that rogue planet clusters are not rare anomalies, but a fundamental component of galactic architecture. We anticipate that future missions, like the Nancy Grace Roman Space Telescope, will completely transform our capacity to study clusters of rogue planets. Improved detection rates and in-depth investigations of their physical features, compositions, and interactions will be provided by these missions. This information has the potential to revolutionize our knowledge of planetary systems, whether they are orbiting stars or floating aimlessly in space. Clusters of rogue planets remind us that the universe is more dynamic and chaotic than we often imagine. These wandering worlds, unbound by the constraints of a stellar system, challenge our perceptions of what it means to be a planet. They force us to think beyond traditional definitions and consider new possibilities for planetary science, interstellar interactions, and even the origins of life. In the end, rogue planet clusters are not just objects of curiosity, they are keys to unlocking the broader mysteries of the universe. Lone pulsars and their emissions beyond galaxy clusters. Transitioning from the fascinating subject of rogue planets scattered through interstellar space, we find ourselves drawn toward an equally mysterious phenomenon: lone pulsars. These isolated remnants of massive stars are far removed from the comforting embrace of galaxies, existing instead in the vast and quiet expanses of intergalactic space. With their powerful magnetic fields and precise rhythmic emissions, lone pulsars offer a unique glimpse into the extremes of astrophysical environments. Lone pulsars begin their lives as part of a stellar system, often in regions densely populated by stars. However, violent supernova explosions can eject these neutron stars, hurling them into intergalactic space with incredible velocities. Some travel over 1,000 kilometers per second, a speed so immense that it can tear them away from the gravitational pull of their home galaxy. The dynamics of this ejection process hold clues about the asymmetry of supernova and the immense forces at play during these cataclysmic events. What makes lone pulsars so compelling is their unmatched regularity in emission. Like cosmic metronomes, they pulse with precise radio, X-ray, or gamma-ray signals. These emissions, though sometimes faint, can traverse billions of light-years, reaching telescopes on Earth. Scientists use this extraordinary consistency to measure vast cosmic distances and probe the composition of the intergalactic medium. The delay or distortion in their signals can reveal the density and structure of intergalactic gas, mapping otherwise invisible regions of the universe. Their magnetic fields are among the strongest in the universe, often exceeding a quadrillion Gauss. This immense magnetic power influences not only their emissions, but also their surroundings. When pulsars travel through intergalactic space, their magnetospheres interact with the sparse material found there, producing observable effects that provide a deeper understanding of intergalactic environments. These interactions can sometimes create trails of ionized gas, known as pulsar wind nebulae, which serve as markers of their motion. Some lone pulsars rotate with astonishing speed. Millisecond pulsars, for example, can complete hundreds of rotations per second. This rapid rotation defies expectations for isolated neutron stars and raises questions about their origins. Were they once part of binary systems that spun them up through accretion before being ejected? Or do they represent a class of neutron stars, born with unusually high rotational speeds? These questions challenge existing theories of stellar evolution and demand further investigation. Lone pulsars are not just static observers of intergalactic space. They are active participants. Their spin-down rates, how their rotation slows over time, offer insights into the loss of rotational energy and the decay of their magnetic fields. This energy loss manifests as electromagnetic radiation, which can illuminate their immediate surroundings and contribute to the ionization of intergalactic gas. These effects extend their influence far beyond their physical boundaries. Unexpected behavior, such as abrupt shifts in emission patterns, is occasionally seen by lone pulsars. The presence of these glitches suggests that the neutron star is involved in intricate activities, which may include the motion of superfluid stuff within. These occurrences, which are similar to circumstances that existed just after the Big Bang, provide a unique glimpse into the mechanics of matter in extremely harsh situations. Their emissions also hold the potential to uncover gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. The precise timing of pulsar emissions allows researchers to detect minute perturbations caused by passing gravitational waves, enabling studies of massive cosmic events like black hole mergers, or even the expansion of the universe itself. The presence of lone pulsars in intergalactic space raises questions about their origins. While many are likely remnants of supernova explosions, others could be relics of galactic mergers or tidal interactions. When galaxies interact, gravitational forces can strip stars from their hosts, leaving them adrift in intergalactic voids. Some lone pulsars might even be survivors of disrupted dwarf galaxies, their solitary existence a testament to the chaotic history of cosmic evolution. These isolated stars, also serve as natural laboratories for studying plasma physics under extreme conditions. Their magnetospheres, rich in charged particles, create environments that replicate the high-energy processes found in particle accelerators. Observing these interactions allows scientists to test theories of plasma behavior and magnetic field dynamics in a setting that cannot be replicated on Earth. Surprisingly, some pulsars that appear to be alone might actually be hiding from us. Despite their cosmic isolation, they may have retained planetary systems or the remains of binary companions. If these friends could be located, we could learn more about their backgrounds and the influences that molded them. From a broader perspective, lone pulsars offer insights into the larger cosmic web. Their precise locations and motions help map the gravitational influences of unseen matter. By tracing their paths, researchers can uncover the hidden structure of the universe, revealing connections between galaxies and the vast voids that separate them. The study of lone pulsars extends beyond their individual characteristics. Their ancient light, traveling for millions or even billions of years, carries information about the state of the universe at different epochs. As such, they serve as time capsules, preserving clues about the conditions that existed long before our galaxy formed. The search for lone pulsars continues to push the boundaries of observational astronomy. Advanced telescopes and radio arrays, such as the Square Kilometre Array, promise to detect even fainter signals, expanding our understanding of these enigmatic objects. As more lone pulsars are discovered, their diversity in spin rates, emission profiles, and environments will undoubtedly refine our models of stellar evolution and intergalactic dynamics. Transitioning from lone pulsars to the vast interplay of galaxies, the mysteries of the universe remain as compelling as ever. Each discovery, whether of a lone star in the emptiness of intergalactic space or the faint glow of a distant hydrogen bridge, adds another layer to our understanding of what lies beyond the solar system. Hypothetical plasma-based life in extreme exoplanet environments. The search for what lies beyond the known universe takes us into the speculative yet fascinating realm of plasma-based life forms, imagined to exist in extreme environments. As we transition from rogue planets clustering in interstellar space, where gravitational anomalies create new groupings, we now consider a type of existence far removed from traditional notions of biology. On certain exoplanets, conditions are so extreme, searing temperatures, immense pressures, and intense radiation, that no organic life form could ever survive. Yet, such environments are fertile grounds for plasma, the fourth state of matter. Plasma is an ionized gas where electrons roam free, creating a highly energetic and dynamic state. In laboratories, plasma exhibits behaviors resembling self-organization, forming filamentary structures and complex systems. Could this be a glimpse into the processes supporting lifelike behaviors? These plasma-rich exoplanets might harbor electromagnetic ecosystems. Unlike biological organisms dependent on water and carbon, plasma entities could utilize electromagnetic fields for sustenance and interaction. Planets categorized as hot Jupiters, orbiting close to their stars and bathed in radiation, could sustain plasma habitats within their atmospheres. Strong magnetic fields, common on such planets, may provide stability to plasma forms. Much like cell membranes provide structure to organic life, plasma life may be able to breathe like cells by exchanging charged particles, which is an interesting prospect. However, ionized gas interactions might be sufficient for these organisms in place of carbon dioxide and oxygen. They would be powered by high-energy cosmic rays or star radiation, which would continuously provide them with the energy they require to stay alive. Aurora-like occurrences, in which charged particles interact with atmospheric components to produce breathtaking light displays, may serve as both a natural spectacle and a habitat for life based on plasma. The dynamic nature of plasma also raises the possibility of communication systems based on electromagnetic signals. Organic life communicates through chemical reactions and electrical impulses. Plasma life, unbound by the slow pace of organic systems, could exchange information almost instantaneously via electromagnetic waves. Such mechanisms would offer a level of adaptability and intelligence that could rival or exceed the complexities of Earth's ecosystems. There may be unprecedented evolutionary routes driven by the variety of chemical components on exoplanets that support plasma life. Plasma fields would be enhanced by heavier elements distributed during star explosions, allowing for complicated ionic interactions, such as those involving hydrogen and helium. This variety has the potential to open new kinds of life, while also resembling the chemical richness required for organic biochemistry. Magnetic confinement zones, naturally occurring due to a planet's magnetic fields, might act as the habitats for plasma entities. Here, stability could allow the development of complex structures over time. On Earth, similar principles are observed in controlled fusion experiments, where plasma is confined within magnetic fields. Extrapolated to a planetary scale, these zones might provide long-term stability for plasma life. The existence of plasma-based organisms presents a significant challenge for observation and detection. Such life forms might emit electromagnetic radiation, but remain invisible in other wavelengths, blending seamlessly with the background cosmic noise. Advanced telescopes and instruments designed to detect faint electromagnetic signals could one day uncover traces of their presence. Space is just one of many possible contexts for this concept. Possible plasma ecosystem hosts include gas clouds, auroras, and areas close to active galactic nuclei. Picture intergalactic gaps spanned by magnetic fields, which would serve as a structure for plasma interactions. These plasma creatures might be sustained by stellar winds that transport charged particles across light years, transforming the vastness into a dynamic network of lifelike actions. Even in the outer reaches of our solar system, plasma activity plays a critical role. The solar wind, an unending stream of plasma from the Sun, interacts with planetary magnetospheres, generating phenomena such as Jupiter's auroras. These interactions provide a small-scale analogy to what might happen on a larger scale in exoplanetary systems or interstellar regions. The concept that plasma life calls into question the nature of life itself is one of its most alluring features. The trinity of carbon, water, and DNA is the traditional definition of life. Existence of plasma-based organisms would redraw these lines, demonstrating that life may arise in environments with self-sustaining energy fluxes and structures. Additionally, they would encourage scientists to investigate abnormalities in electromagnetic signals, ionized gas distributions, or auroral patterns, thereby expanding our search criteria for extraterrestrial life. Consider the hypothetical implications of plasma life in relation to cosmic evolution. If such entities existed, they might interact with the environments around them in ways that influence the formation of stars, planets, or even galaxies. Their existence could create feedback loops, where energy from their metabolism contributes to cosmic processes. Much like organic life alters Earth's biosphere, there are some very deep philosophical concerns raised by the idea of plasma life. Is awareness possible in a world where energy and electromagnetic forces may give rise to life? Experiments with plasma in a controlled environment reveal intricate characteristics, such as the ability to mend itself and react to outside influences. These don't even come close to what we're aware of, but they do suggest avenues we're just starting to investigate. The search for plasma-based life forms aligns with the broader themes of our cosmic exploration. Just as we examine faint halos of rogue planets clustering in interstellar voids, we now look for entities that might thrive where energy, not matter, is the primary building block. These ideas connect to the fundamental curiosity driving humanity's exploration of the unknown, understanding our place in an unimaginably vast and diverse universe. Future missions might focus on detecting electromagnetic patterns or high-energy anomalies around exoplanets and interstellar regions. Observatories equipped to study plasma interactions, like those monitoring solar winds or auroras, could be adapted to search for lifelike signals in alien environments. Meanwhile, experiments here on Earth, using plasma confinement and self-organization models, might reveal principles applicable to hypothetical plasma ecosystems elsewhere. As we shift our focus to other phenomena beyond the solar system, the possibility of plasma-based life reminds us how adaptable and creative nature can be. These entities, if they exist, might not only challenge our scientific understanding, but also expand our perspective on what it means to be alive. In this cosmic journey, every discovery, whether a planet orbiting a distant star or an electromagnetic anomaly in the depths of space, adds another thread to the intricate tapestry of what lies beyond the universe we know. Fossil galaxy remnants in the Milky Way's halo. Far out in space, in the Milky Way's halo, there are remnants of long-gone galaxies that were engulfed by our own. A unique opportunity to learn about the early universe and beyond is presented by these dispersed and occasionally weak fossil galaxy remnants. The history of the universe as we know it is molded by the shards preserved by each relic, which tell stories unique to each one. Rather than just existing, these ancient structures testify to the complex and violent dance of galaxy development. Unlike the bustling galactic core, these remnants are found far out in the halo, where the density of stars begins to thin, but the intrigue deepens. Their chemical signatures are like fingerprints, offering clues about their origins and the conditions that defined their early years. In some cases, stars in these remnants show chemical compositions that are entirely distinct from the Milky Way's typical stellar population. High metallicity variations in their stars suggest environments rich in heavy elements, hinting at a history of rapid star formation before these galaxies were consumed. Stellar streams, often observed stretching across the halo, reveal the raw mechanics of these mergers. The Sagittarius stream is one of the most studied examples, a tidal remnant of a dwarf galaxy pulled apart by the Milky Way's gravity. As these smaller galaxies approach the Milky Way, tidal forces stretch them into long streams of stars that eventually disperse and become part of the halo. These remnants don't just disappear. Their stars become the building blocks of a larger, more complex system. The orbits of these stars often carry an elliptical shape, unlike the more uniform motions of stars in the galactic disk. This irregular movement reflects the violent gravitational interactions that tore their host galaxies apart. Each orbit is like a fossilized echo of the merger that brought them here, preserving a record of the Milky Way's insatiable growth over billions of years. Some of these remnants still retain a semblance of their original structure, while others are almost entirely dissolved, their stars blending into the broader halo. Ultra-faint dwarf galaxies, barely visible against the backdrop of interstellar space, represent the faintest of these remnants. They are like cosmic relics, offering the most pristine views into the conditions of the early universe. Their stars, some of the oldest ever discovered, are living fossils, formed just after the first few 100 million years of the cosmos. These faint remnants hold clues to the initial bursts of star formation that ignited the universe's evolutionary journey. Advanced imaging technologies have become essential in uncovering these elusive structures. Instruments like the Gaia Space Observatory have mapped the positions and movements of billions of stars, revealing intricate streams and clusters that were previously hidden. These observations have redefined how we see the Milky Way, not as a static entity, but as a living system shaped by countless interactions with other galaxies. Each stream and cluster adds a piece to the puzzle, revealing the Milky Way's long history of mergers and acquisitions. The chemical compositions of these remnants are particularly enlightening. Certain elements like europium or barium are found in higher concentrations in some fossil galaxies, suggesting they underwent unique nucleosynthesis processes before merging with the Milky Way. These variations tell a story of diverse galactic environments, where supernovae and neutron star collisions forged heavy elements in abundance. Some remnants harbor dense objects like black holes, relics of their former galactic cores. These hidden features add another layer of complexity, suggesting that even the smallest galaxies could have hosted massive gravitational wells at their centers. As these remnants merged with the Milky Way, their black holes may have been incorporated into the galaxy's broader structure, potentially feeding the supermassive black hole at the Milky Way's core. Computational models have become indispensable for simulating these interactions. By studying how smaller galaxies are stripped of their stars and gas during mergers, researchers can better understand the dynamics that shape the Milky Way. These models reveal that galactic mergers not only add stars, but also redistribute gas, influencing the formation of new stars in the larger galaxy. The remnants of these mergers become part of a cycle of cosmic recycling, where material from one galaxy is used to build another. The fossil record of the Milky Way doesn't just include stars. Globular clusters, dense groups of stars often found in the halo, are thought to be remnants of these smaller galaxies. Many globular clusters show properties that suggest they formed in environments very different from the Milky Way, further supporting the idea that they are galactic immigrants. Some clusters, like Omega Centauri, are so massive and unique that they may represent the cores of dwarf galaxies, stripped of their outer stars. Beyond their scientific significance, these fossil galaxies challenge our perception of the universe's vastness and its interconnectedness. They show that no galaxy exists in isolation. Every interaction leaves an imprint, shaping not only the galaxies involved, but also the broader cosmic landscape. Even as these remnants are absorbed into the Milky Way, their individuality persists, etched into the motions, compositions, and structures of their stars. The Magellanic Stream, a gas bridge that links the Milky Way to the large and small Magellanic Clouds, is one of the structures that we discover when we probe further into the halo. This structure is not a fossil galaxy per se, but it does exhibit the same kind of continuous interactions that gave rise to such galaxies in the past. These streams point to potential future mergers, when these dwarf galaxies might end up as fossils in the Milky Way. The study of fossil galaxies isn't confined to the Milky Way. Nearby galaxies like Andromeda show similar signs of having consumed smaller galaxies. Comparing these systems helps astronomers build a universal model of galactic growth, where mergers are not the exception, but the rule. This perspective transforms the Milky Way from a single galaxy to a participant in a much larger cosmic web of interactions. Fossil galaxies are also crucial for understanding the universe's early epochs. By studying their oldest stars, astronomers can infer conditions in the universe shortly after the Big Bang. These stars are like time capsules, holding within them the chemical and physical properties of the early cosmos. The fact that these remnants have survived for billions of years, despite the chaos of mergers and interactions, speaks to the resilience of their structures and the information they contain. These ancient remnants are not just historical artifacts, but active contributors to the Milky Way's evolution. As their stars mix with the galaxy's own, they enrich the halo with new materials, seeding future generations of stars. The mergers that brought these remnants into the Milky Way may have also triggered bursts of star formation, contributing to the vibrant stellar population we see today. One thing we can learn from fossil galaxies is that our Milky Way isn't finished yet. Interactions, mergers, and transformations between galaxies are ongoing processes in an ever-changing cosmos. The history and future of the Milky Way are being pieced together with each fresh finding in the halo. These relics provide insight into an earlier, more formative period of the cosmos by bearing testimony to the cosmic processes that formed our galaxy. High-speed stellar streams on the edge of our galaxy. The remnants of disrupted galaxies and clusters scattered across the outskirts of the Milky Way provide a vivid snapshot of the dynamic forces shaping our cosmic environment. High-speed stellar streams exemplify the result of these interactions, as these clusters of stars, stripped from their progenitors by gravitational forces, now traverse the galaxy's edges. They serve as a key to understanding how the Milky Way grew, absorbing smaller galaxies over billions of years. These streams, moving at speeds surpassing 500 kilometers per second, are not just remnants, but active traces of the unseen forces that govern the galaxy's structure. The Sagittarius Stream, one of the most extensively studied examples, stretches across the sky, tracing the orbital path of the Sagittarius dwarf galaxy as it was torn apart by the Milky Way. This stellar stream is a map of past interactions, marking each passage of the dwarf galaxy as it lost stars and eventually dissolved into the larger system. Newer discoveries, like the Orphan Stream, lack a clear progenitor, suggesting that its original system may have been completely dismantled or even scattered so widely that its core is now unrecognizable. This raises intriguing questions about the limits of tidal disruption and how small galaxies and clusters lose cohesion when interacting with a much larger host. There are instances where these streams show interactions that don't include our galaxy. As an illustration of continuous accretion, consider the Magellanic Stream, which is connected to the Large and Small Magellanic Clouds. The Milky Way is still reshaping its periphery by absorbing material from surrounding systems, according to its connections to these satellite galaxies. That galaxies undergo continuous evolution as a result of mergers and accretions is supported by this process, which is continuing. Stars traveling at such high speeds that they are able to evade the gravitational pull of their galaxy are known as hypervelocity stars, and they are found in certain stellar streams. Interactions with compact objects or black holes in the streams may have expelled these stars. Their existence suggests that the streams may still include intermediate mass black holes, which are relics from the initial parent systems. The chemical compositions of stars in these streams often reveal details about their origins. For example, variations in metallicity across a stream can indicate multiple generations of star formation within the progenitor galaxy. Streams with chemically uniform stars likely originated from smaller, simpler systems like globular clusters. Conversely, those with diverse compositions may point to disrupted dwarf galaxies with more complex star formation histories. The gravitational effects of the streams on their surroundings tell a fascinating story. As these stars move through the Milky Way's halo, they occasionally interact with the galactic disk, causing shifts in trajectory. Some streams even show evidence of interacting with other streams, creating localized regions of star formation. These interactions demonstrate the interconnected nature of cosmic structures, where even remnants of past collisions can spark new activity. The Nix stream, a recently identified structure with an orbit inclined to the plane of the galaxy, provides evidence of an extragalactic origin. Its unique trajectory suggests it may have been captured during one of the Milky Way's early interactions, offering a glimpse into the chaotic process of galactic growth. Streams like Nix challenge us to reconsider how many of the Milky Way's features were not born within, but rather acquired through cosmic mergers. Even streams that have settled into more stable orbits continue to evolve dynamically. Over time, the stars within these streams disperse, blending into the Milky Way's stellar halo. In a sense, the streams are fleeting records of interactions that will eventually disappear. This blending process speaks to the transient nature of cosmic structures. Distinct features today may be unrecognizable in a billion years. The detection of these weak streams has been greatly aided by technological advancements. Thanks to Gaia and other instruments, we can now monitor star locations and movements with unprecedented precision, and streams that were previously undetectable are now readily apparent. Because of this, there has been a dramatic increase in the number of findings that fill out the complex map of the Milky Way's periphery. Even the gravitational effects of the Milky Way's bar and spiral arms can leave imprints on streams, altering their trajectories and creating unexpected patterns. These perturbations help refine models of how the galaxy's internal structures interact with its halo. Polar orbiting streams further complicate matters. Diverse merger scenarios are indicated by their perpendicular paths, which point to beginnings beyond the main plane of the galaxy. Mergers are commonly believed to occur mostly in the galactic plane. However, these streams cast doubt on that assumption. Despite their dynamism, the long-term fate of these streams is one of eventual dispersal. As their stars continue to drift apart, the distinct structures will fade, becoming indistinguishable from the Milky Way's background star population. Yet, even as they vanish, the evidence of their presence will remain in the stars themselves, carrying the chemical and kinematic signatures of their origins. Looking beyond the Milky Way, similar streams have been observed in neighboring galaxies, suggesting that the processes shaping our galaxy are universal. By studying these extragalactic streams, we gain insights into how galaxies grow and evolve across the universe. High-speed stellar streams represent the ongoing narrative of the Milky Way's formation. They are the echoes of past collisions, the markers of unseen forces, and the architects of future galactic structures. Neutrinos from beyond the solar system. The detection of neutrinos, those tiny, nearly massless particles that travel at almost the speed of light, has become one of the most intriguing tools for exploring the universe. While their elusive nature makes them difficult to study, the data they carry has the potential to transform our understanding of events and processes that remain hidden from traditional observation methods. When gamma-ray bursts occur, they unleash massive amounts of energy in a fraction of a second. These bursts are not only brilliant in gamma rays, but also produce high-energy neutrinos. Unlike gamma rays, neutrinos escape their origins without scattering or absorption, carrying a direct imprint of the processes driving these explosions. The neutrinos detected from these bursts have provided insights into the energy levels required to power such cosmic spectacles, offering glimpses into the life and death of some of the universe's most massive stars. Colliding neutron stars generate neutrinos in their violent interactions. When these dense remnants of supernovae crash into one another, the event releases a shower of neutrinos alongside gravitational waves. These neutrinos provide information about the conditions under which heavy elements like gold and platinum are formed. Observing such collisions has given scientists a new perspective on how matter behaves under extreme density and pressure, conditions impossible to replicate on Earth. Deep beneath the ocean, neutrino detectors such as Antares and KM3net use seawater to track the faint signals of these particles. Unlike traditional observatories, these underwater experiments leverage the ocean's natural clarity and depth to detect neutrino interactions. The unique setting allows researchers to identify neutrinos originating from distant astrophysical sources, revealing pathways for these particles that stretch across cosmic scales. Neutrinos produced in pulsar wind nebulae are another source of valuable data. Pulsars, spinning remnants of massive stars, emit winds of charged particles at nearly the speed of light. When these winds collide with surrounding material, neutrinos are generated. By analyzing these neutrinos, scientists gain insights into how pulsars transfer energy to their surroundings, creating nebulae that glow with high-energy emissions. Solar flares, massive eruptions on the sun's surface, also generate neutrinos. These events occur when magnetic fields on the sun suddenly realign, accelerating particles to high energies. The neutrinos produced during these flares provide clues about the sun's magnetic activity and the processes that drive these energetic bursts. Such observations not only deepen our understanding of the sun, but also reveal the mechanisms of particle acceleration in our solar system. Tidal disruption events occur when a star ventures too close to a supermassive black hole and is torn apart by tidal forces. These violent interactions emit neutrinos, which escape the chaos and travel across the cosmos. Observing neutrinos from these events helps scientists understand the extreme conditions around black holes, revealing processes that are otherwise invisible in the electromagnetic spectrum. Earth is now a huge lens for neutrino tomography. Researchers have mapped the interior structure of Earth by examining the transit of neutrinos. This approach provides a non-invasive method for studying materials and conditions deep beneath the surface of the Earth by allowing scientists to peek into the mantle and core without digging. The interaction of neutrinos with polar ice sheets is another innovative research area. Antarctic observatories such as IceCube use the transparency of ice to detect faint flashes of light caused by neutrino interactions. These signals provide a direct link to distant cosmic events and preserve information from ancient epochs of the universe. On other planets, neutrino interactions with atmospheres offer unique data about their compositions. When neutrinos collide with molecules in a planet's atmosphere, they leave traces that can reveal the presence of specific elements or compounds. This approach could provide an entirely new method for studying exoplanets and their habitability. Starburst galaxies, regions of intense star formation, are prolific sources of neutrinos. The high-energy processes driving the formation of massive stars and their explosive deaths produce neutrinos that travel across the universe. By studying these neutrinos, scientists can explore how starburst activity shapes the evolution of galaxies. Stellar winds from massive stars also create neutrinos as they interact with interstellar material. These winds, composed of charged particles, collide with surrounding gas and dust, generating neutrinos that carry information about the star's life cycle. Lunar eclipses provide rare opportunities to observe neutrinos under unique conditions. During these eclipses, the alignment of the Sun, Earth, and Moon alters the paths of neutrinos traveling through space. Studying these variations enhances our understanding of neutrino interactions and their behavior in different environments. The study of ancient ice cores has revealed an unexpected application for neutrino science. By analyzing neutrino interactions preserved in glacial ice, scientists can uncover clues about cosmic activity during Earth's ice ages. These frozen records offer a glimpse into the universe's past and its impact on our planet. In volcanic regions, neutrino detection experiments investigate interactions between these particles and magma. Neutrinos passing through volcanic material reveal variations in density and composition, providing data on volcanic activity and the movement of magma chambers. Regions with high rates of supernova create distinct patterns of neutrino emissions. These supernova factories serve as natural laboratories for studying the explosive ends of massive stars. Observing the neutrinos from these regions has deepened our understanding of how supernovae contribute to the enrichment of galaxies. Patterns left by neutrinos in glacial ice offer a physical record of their journey through the universe. These tracks, preserved for millennia, provide direct evidence of cosmic processes and serve as time capsules of ancient astrophysical events. When stars merge, they emit neutrinos that capture the energy and processes involved in these dramatic events. These emissions reveal the physics behind stellar mergers and the resulting cosmic phenomena, such as gravitational waves. Seasonal variations in neutrino detection rates have revealed periodic changes in Earth's position relative to neutrino sources. These fluctuations offer insights into the distribution of neutrino-producing phenomena across the universe. Extreme conditions, such as those found in dense stellar environments, test the limits of neutrino interactions. Experiments conducted in such settings provide valuable data on how neutrinos behave under pressures and temperatures far beyond what can be achieved in laboratories. Underwater neutrino tracks, recorded by oceanic detection arrays, form patterns that point to their cosmic origins. These patterns help researchers identify the sources of neutrinos and reconstruct their paths across the universe. By passing through planetary interiors, neutrinos offer indirect imaging of their compositions. This method could be used to study the internal structures of planets both within and beyond our solar system. Neutrinos from dying stars provide real-time data on the stages of stellar collapse. These particles reveal how energy is released during these dramatic events, offering a direct link to the processes behind supernovae and other star deaths. Galactic collisions generate neutrino emissions that reflect the energetic interactions between merging galaxies. These signals provide data on how galaxies evolve and transfer energy during their mergers. Rapid neutrino bursts associated with space weather phenomena create opportunities for real-time observation. These flashes, linked to energetic processes like solar storms, help scientists study the dynamic behavior of particles in our solar system. Antarctic neutrino observatories have inadvertently tracked the movement of glacial ice while detecting neutrinos. This dual-purpose data offers new perspectives on both cosmic events and Earth's changing environment. High-energy neutrinos detected in star clusters offer insights into interactions between stars and interstellar matter. These emissions reveal how energy and particles are distributed in dense stellar environments. The processes that create chemical elements in stars leave traces in the neutrinos they emit. By studying these particles, scientists gain a deeper understanding of how stars contribute to the cosmic abundance of elements. Neutrinos' ability to travel through dense regions of intergalactic space makes them ideal probes of the unseen matter between galaxies. These particles map the distribution of matter and energy in the universe, revealing structures invisible to traditional telescopes. High-energy cosmic events that emit unexplained bursts of neutrinos challenge existing astrophysical models. These rare detections point to phenomena that remain mysterious, pushing the boundaries of what we know about the universe. The energy transfer, facilitated by neutrinos across vast cosmic distances, links dispersed regions of the universe. By studying this transfer, scientists can trace the connections between seemingly isolated astrophysical phenomena. Certain binary star systems emit neutrinos through interactions between their closely orbiting components. These emissions reveal the dynamics of binary systems and the processes that govern their evolution. Neutrino signals from billions of years ago provide a time capsule of ancient cosmic events. These particles, traveling uninterrupted through space, preserve a record of the universe's earliest moments, connecting us to its origins. The cosmos is an endless canvas of mystery, painted with phenomena that challenge our understanding of reality. As we peer beyond the familiar, exploring stellar streams racing across the galaxy's edge and ancient fossil galaxies hidden in the Milky Way's halo, we begin to glimpse the vast interconnectedness of the universe. These discoveries remind us that what lies beyond the solar system, and even the universe itself, isn't just distant and unreachable. It's a story unfolding in real time, shaping the very fabric of existence. I hope you enjoyed the video. If you did, feel free to subscribe to the channel. Thanks for watching.